Hello there, and welcome to Simply About Earth, where curiosity takes its time and science finds its rhythm. Tonight, we're drifting gently into a version of our planet that most of us never pause to consider. It's not the Earth of satellite images or weather forecasts, not the one with sprawling cities, vast forests, deep blue oceans, and the familiar hum of life. This Earth is older than history itself, older than bones, older than oxygen, older even than the concept of breathing. It's the Earth of the Archean Eon, a time so distant that the ground beneath our feet today hadn't quite decided what it wanted to become. This was a world without animals, without plants, without anything you could recognize as familiar. The sky wasn't blue, the air wasn't safe to breathe, the sun was dimmer, casting its light through alien atmospheres. Days passed more quickly. The oceans were strange, filled with elements that would poison any modern fish. And yet, this was the beginning, not the very beginning of Earth itself, but the beginning of what we can trace back through time, the start of the oldest rocks still standing, the first fragments of what would become continents, and somewhere in all that chemical chaos, the earliest sparks of life. Before we dive deeper into this ancient world, I'd love to know where you're watching from tonight. Drop a comment and let me know what corner of the world you're exploring the past from. Whether you're in a bustling city or a quiet countryside, we're all connected by the same planetary story. It's strange to imagine this ancient Earth because everything we take for granted, breathing, walking, growing food, building homes, requires a planet that came much, much later. But if we want to understand how we got here, we have to start back there. In that alien time, the Archean wasn't quiet or simple. It was active, volcanic, unstable, and constantly reshaping itself. But that restless energy is exactly what makes it worth exploring. It wasn't a peaceful memory locked away in the past. It was a long, slow conversation between heat and water, between rock and time, between chemistry and the first tentative experiments in biology. So wherever and whenever you're listening from, whether it's evening, early morning, or somewhere in between, take a moment to settle in. Let your thoughts slow just a bit. We're not rushing through this story. We're going to let it unfold at the pace the Earth itself set. Slow, steady, and full of surprises. The Archean isn't just a chapter in our planet's deep history. It's the first part we can still read in the rocks around us. The first time Earth left a record we can decipher. So let's begin there, in a time before trees existed, before breathable air filled the atmosphere, before even the word Earth would have meant anything at all. At the start of the Archean, roughly 4 billion years ago, Earth was still in what we might call recovery mode, not from civilization or climate change as we understand them today, but from its own violent birth. The planet had formed just a few 100 million years earlier, pulled together from the dust and debris orbiting our young sun. It had already survived at least one catastrophic impact, the collision that formed the Moon, an event so massive it reshaped the entire structure of our world. Heat from these collisions, combined with energy from radioactive decay deep in the core, left the early Earth glowing from the inside out. By the time the Archean began, things were starting to cool, but only just. The crust had begun to solidify, though it wasn't the thick, stable surface we know today. Instead, it was more like a restless shell, thin in places, broken in others, constantly cracking open and recycling itself back into the molten interior. Volcanoes weren't just scattered here and there across the landscape. They were everywhere. Entire regions were dominated by volcanic activity, with magma rising from below and reshaping the surface again and again. Above this unstable foundation was an atmosphere that would have been toxic to anything alive today. It was dense and hot, filled with gases from volcanic outgassing, carbon dioxide, methane, ammonia, water vapor, and other compounds that painted the sky in unfamiliar colors. Oxygen, the kind you're breathing right now, was almost completely absent. If you had somehow managed to stand on that ancient surface, there wouldn't have been much to see beyond thick clouds and perhaps the dim outlines of volcanic islands rising from vast, dark oceans. you wouldn't have lasted more than a few breaths, not because the planet was dead, but because it was just getting started. The oceans were already in place by the early Archean, though their origin remains one of geology's great debates. Some scientists believe water arrived from icy comets that bombarded the planet during its chaotic youth. Others think the water was always here, trapped in minerals deep inside the earth and released slowly over time through volcanic outgassing. However it arrived, water was a major player in the story from the very beginning. It covered most of the surface, interrupted only by scattered volcanic landforms and fragments of early crust. And those oceans weren't the clear blue you might picture when you think of water. Without oxygen, iron dissolved freely, giving the seas a darker, possibly greenish or reddish hue. Combined with the hazy atmosphere and weaker sunlight, the world would have looked completely alien, dimmer, heavier, and much more volatile than anything we can easily imagine. Despite all that apparent hostility, this was a world absolutely brimming with chemical potential. The combination of heat, minerals, gases, and liquid water created countless opportunities for molecules to collide, react, and evolve into more complex forms. Somewhere in this chemical mix, life began. We don't know exactly when or how. The details remain uncertain, and may always be so. But by the middle of the Archean, around 3.5 billion years ago, there's evidence that life was already established. Not plants or animals, not even complex cells. These were microbial organisms, single-celled, and incredibly simple by today's standards, but capable of growth, reproduction, and metabolism. They lived in the oceans, likely in shallow, warm environments rich in minerals and energy sources. Some clung to rocks, others floated freely, and many gathered around hydrothermal vents where superheated water flowed from cracks in the seafloor. The earliest life forms may not have relied on sunlight at all. Instead, they might have used chemical energy from the Earth itself, through a process we call chemosynthesis. These organisms harvested energy by breaking down hydrogen sulfide, methane, or other compounds found near underwater vents. Even today, similar ecosystems still exist at the bottom of modern oceans, home to organisms that don't need light to survive, just chemistry and time. Eventually, something remarkable happened. Some of these microbes figured out a way to use sunlight, even in the dim skies of the early Earth. This process, photosynthesis, began to reshape the entire planet, though very, very slowly. At first, it didn't produce oxygen. Early forms of photosynthesis likely used hydrogen or sulfur compounds instead. But over time, a new form emerged, oxygenic photosynthesis, carried out by organisms known as cyanobacteria. These microbes were the first to release oxygen as a byproduct of capturing sunlight. They did it slowly, and at first the oxygen didn't build up in the air. It reacted with iron dissolved in the oceans, forming rust-like minerals that sank to the seafloor. These iron-rich layers eventually became what we call banded iron formations, geological evidence, still visible today, that oxygen was starting to change the chemistry of the planet. Back on the surface, the continents, or what would eventually become continents, were beginning to form. The process was uneven and slow. Instead of large land masses, there were small pieces of crust, sometimes called protocontinents, scattered like puzzle pieces not yet assembled. These fragments formed through repeated cycles of volcanic activity, cooling, and crustal thickening. As they collided and fused together, they began to grow into more stable blocks. The ancient cores of today's continents, known as cratons, are among the oldest parts of Earth's crust, and many date back to the Archean. You can still find them today in places like Canada, Australia, South Africa, and parts of Scandinavia. These regions have remained geologically stable, having survived billions of years of tectonic activity, erosion, and metamorphism. When geologists study these ancient cratons, they're looking directly into Earth's deep past, examining the same surfaces that once floated as islands in Archean seas. The movement of these crustal fragments may have resembled early plate tectonics. though the details remain a topic of ongoing research and debate. Modern plate tectonics as we understand it today, with rigid plates moving over a viscous mantle, may not have been fully active yet. The Archean Earth was much hotter, which could have made the crust more pliable and the boundaries between plates less clearly defined. Still, there's evidence of subduction, collision, and crustal recycling, all of which suggest a dynamic, evolving planet responding to forces from deep within. Meanwhile, the length of a day on Earth was shorter than it is now, somewhere around 14 to 16 hours. That's because the Earth was spinning faster, a result of its initial momentum after formation. Over time, the Moon's gravitational pull created tidal forces that gradually slowed our planet's rotation. But during the Archean, the world turned more quickly, and those shorter days affected everything from weather patterns to the behavior of ocean tides. The Moon itself, newly formed and still moving away from Earth, would have appeared much larger in the sky. Its gravitational influence was stronger, pulling at the oceans and contributing to powerful tides that were far more dramatic than anything we see today. These tides may have helped mix the oceans, driving chemical reactions and supporting the development of early life. They also influenced erosion and sedimentation patterns along the shorelines of those ancient seas. Magnetic fields were already in place by this time, generated by the motion of molten iron in Earth's outer core. This magnetic field protected the planet from solar radiation even in its early state, and may have played a crucial role in preserving the atmosphere and shielding life from harmful particles. The field wasn't as strong or as stable as today's, but it existed, another early step in the planet's long journey toward habitability. One thing you wouldn't have found on this early Earth was sound in the way we think of it. There were no birds, no insects, no rustling leaves or animal calls. The world was quiet in a way that's almost impossible to imagine now. The sounds were geological, volcanic eruptions, ocean waves crashing against bare rock, the occasional cracking of the crust. But there were no biological sounds. Life didn't yet make a sound. That would come much, much later. The climate was variable, influenced not only by the faint young sun but also by shifting greenhouse gas levels. With little land to affect atmospheric circulation and no complex ecosystems to regulate the carbon cycle, temperature swings may have been more extreme both locally and globally. There's evidence for hot conditions in many places, but also signs that parts of the Earth may have experienced cooler climates, perhaps even limited glaciation in some regions. The balance between volcanic outgassing and chemical weathering would have played a major role in regulating the climate. As for the surface itself, it was utterly barren. There were no plants to hold soil in place, no roots to break rocks apart, no organic material to build up over time. The landscapes were shaped entirely by wind, water, heat, and tectonics. Rain would fall, forming rivers and streams, but with nothing to slow erosion. Sediments moved quickly and were deposited in layers that would eventually harden into rock. These early sedimentary rocks, when they survived the test of time, recorded the shapes of an empty world, the quiet movement of water and the slow accumulation of material on the seafloor. And yet, even in that silence, the Earth was moving forward. Every volcanic eruption, every chemical reaction in a tide pool, every new microbial lineage marked a step in a process that would eventually lead to everything we know, the air we breathe, the continents we live on, the ecosystems we depend on. The Archean wasn't a footnote in Earth's history. It was the first sustained act of our planet's transformation, setting the stage for the world to come. We don't need to rush past it or dismiss it as some primitive prelude. There's still so much to uncover in those ancient oceans, in the first raindrops, in the way rock and water began their long relationship that continues today. The crust was growing thicker, the seas were shifting and evolving, and life, however small and simple, had made its entrance onto the stage, and just ahead, the world would begin to change in ways that could no longer be reversed. The quiet beginnings were starting to echo through deep time, and from here we can keep following where those echoes lead. By the time early microbial life had started to establish itself in the oceans, the world above the surface remained entirely inhospitable to anything we'd recognize as life today. The atmosphere of the Archean Earth was thick, alien, and completely unbreathable by modern standards. There was no oxygen to speak of, not in the air, not dissolved in the water, not even stored in minerals near the surface. It was a planet without breath, at least not the kind we understand. The dominant gases were mostly carbon dioxide, methane and nitrogen, with smaller amounts of ammonia, hydrogen, water vapor, and various sulfur-based compounds from volcanic activity. These gases didn't come from biology but from geology, released through volcanic eruptions, outgassing from the mantle, and chemical reactions at the surface. The Earth's early mantle was much hotter and more chemically active than today's, far more prone to releasing volatile compounds into the atmosphere. This ongoing exchange between the planet's interior and its atmospheric envelope was one of the main drivers of the early climate. The atmosphere itself was much denser than what we experience today. There's no exact measurement for surface pressure during the Archean, but models suggest it may have been several times higher than current levels. The high carbon dioxide content would have created a powerful greenhouse effect, which was necessary, since the sun was still significantly dimmer than it is now. Without that insulating layer of gases, Earth's surface would have been frozen solid. Instead, the thick atmosphere trapped enough heat to keep the oceans liquid and maintain surface temperatures above freezing. Still, this wasn't a comfortable balance by any means. Surface temperatures were likely higher than today's global average, though probably below the extreme conditions that prevailed during the earlier Hadean period. Local conditions would have varied widely depending on volcanic activity, ocean circulation, and cloud cover. The sky itself may have had a different hue, possibly an orange or reddish tint, due to the scattering effects of the dense, dusty atmosphere and the complete absence of ozone to filter sunlight. Ultraviolet radiation from the sun would have reached the surface much more easily than it does now. Without an ozone layer, which today forms through interactions between oxygen and UV light, there was nothing to block the more harmful parts of the solar spectrum. Any early life that existed would have needed protection, either by living underwater, hiding in mineral crevices, or developing resistance to UV exposure through chemical means. It's one reason why deep-sea hydrothermal vents and shallow marine sediments are considered the most plausible cradles for early biology. They offered both chemical energy and physical shelter at a time when the surface world was still quite dangerous for living things. The absence of oxygen also meant that there was no oxidative weathering on land, no rust-colored soils, no oxidized minerals, none of the geochemical processes we associate with modern carbon and oxygen cycles. The chemical reactions that shaped the land and water were fundamentally different from what we see today. Iron, for example, remained dissolved in the oceans, giving the water its distinct color and feeding into a global process that would eventually produce those layered iron deposits, banded iron formations, once oxygen began to accumulate even in trace amounts. This slow interaction between the atmosphere, oceans, and crust began laying the groundwork for future changes. Microbial life, particularly early photosynthetic organisms, would start to alter the chemistry of their environment bit by bit. Even before oxygen became a major component of the atmosphere, life was already influencing the balance of gases, cycling carbon, producing methane, and participating in reactions that subtly reshaped the world around them. Methane played a particularly interesting role in this early atmosphere, produced by microbes known as methanogens. This gas is a far more potent greenhouse agent than carbon dioxide. In a world with limited oxygen and abundant carbon sources, methane likely accumulated in significant quantities, reinforcing the planet's ability to retain heat despite the dim sun. There's even speculation that methane haze, created when methane concentrations became high enough, could have affected both the climate and the appearance of the sky, similar to the way Titan, Saturn's largest moon, appears through its thick atmosphere today. Such hazes could have cooled the planet by reflecting sunlight, counteracting some of the warming effect of greenhouse gases. This back and forth between warming gases and cooling haze, a dynamic tension between competing effects, may have created periods of climate instability. Sudden shifts from warmer to cooler conditions and back again, these early feedback loops were primitive versions of the complex climate regulation systems that would evolve over billions of years, ultimately leading to the relative stability of the modern Earth. Despite its volatility, this atmosphere wasn't chaotic in the sense of constant random change. It was stable on long time scales, with patterns, cycles, and chemical pathways, just not the ones we're familiar with today. It lacked oxygen, but it had its own internal logic, driven by geology, by the heat of the planet's interior, by solar radiation, and eventually by the earliest stirrings of biology. The air as it existed then formed a system that supported the planet's chemistry and buffered its temperature, even if it couldn't yet support animals or plants. We sometimes think of oxygen as the most important gas for life, but for the first half of Earth's history, it was either absent or actually a threat to living things. Oxygen is highly reactive, and in a world without it, life evolved along different pathways, using sulfur, nitrogen, or iron as electron donors and acceptors in metabolic processes. When oxygen did begin to appear, even in small amounts, it would have been toxic to many of the organisms that had adapted to the anoxic environment. What eventually became our lifeblood started out as a pollutant. This shift didn't happen all at once, of course. For most of the Archean, oxygen produced by photosynthetic microbes didn't reach the atmosphere in large quantities. It was absorbed by iron in the oceans, by reduced minerals on land, or simply broken down by reactions with volcanic gases. The Earth had a vast oxygen sink, a giant chemical sponge constantly soaking up this new molecule before it could accumulate in the air. It wasn't until these sinks began to fill up, late in the Archean and into the Proterozoic, that oxygen started to build up in the atmosphere, leading to what's now known as the Great Oxidation Event. But that transformation was still far ahead. For the time being, the Archean atmosphere was thick, heavy, and utterly alien by our standards. It was more than just a blanket of gases. It was a chemical machine, one that exchanged energy, filtered radiation, and fed the first ecosystems, even if indirectly. It didn't look like ours, it didn't function like ours, but it worked, and more importantly, it left behind clues. Traces of that ancient atmosphere survive in rocks, bubbles trapped in minerals, isotopic ratios in sedimentary layers, chemical signatures of microbial metabolism. All of these tell us something about what the air was made of and how it changed over time. We can't go back and sample the Archean atmosphere directly, of course, but through geochemistry we can reconstruct parts of it, enough to get a picture, if not a perfect snapshot. Some of the most important evidence comes from sulfur isotopes. In the absence of oxygen, sulfur underwent specific reactions that leave a distinct isotopic fingerprint. These signals show up in Archean rocks but disappear after oxygen levels rise, making them a reliable marker of atmospheric conditions. When we study rocks from different times and places in the Archean, we can see how the balance of gases shifted, how localized changes occurred, and how the planet moved gradually toward a new kind of atmosphere. It's easy to overlook the importance of a planet's air. We breathe it constantly but rarely think about where it came from or how it evolved. Yet in the Archean, the atmosphere was not just a passive environment. It was an active participant in Earth's transformation. It controlled the temperature, dictated the chemistry of the oceans, and set the stage for which life forms could exist and how they could evolve. Without oxygen, there were limits. Large, complex life was impossible, but within those limits, the early Earth found a way to move forward. The atmosphere, strange as it was, provided the conditions for life to persist, to replicate, to innovate, and eventually to reshape the very air itself. It was a planet learning how to breathe, not with lungs or leaves, but with chemistry and time, and as the oceans began to reflect those changes, as new layers of rock started recording the first faint whispers of oxygen in the system, The world inched closer to something genuinely new, not a sudden leap forward, but a slow rebalancing, a quiet evolution happening molecule by molecule, tide by tide. The atmosphere wouldn't transform overnight, and life wouldn't either, but the direction was already set. The Earth wasn't static, it was already preparing for the next chapter, when tiny organisms would leave visible marks and the story of life would finally break the surface. If you're enjoying this journey through deep time so far, I'd love it if you could hit that like button to let me know. It really helps the channel and lets me know that these long-form explorations into Earth's history are connecting with you. Beneath the heavy skies and quiet oceans of the Archean, the Earth's interior was anything but still. The planet was hot, not just warm but deeply structurally heated from the inside out. That internal heat wasn't a leftover annoyance from formation. It was a dominant force shaping every aspect of the planet's early behavior. Volcanism wasn't occasional. It was constant. The surface wasn't settled. It was shifting, flexing, breaking open, and reforming again and again in cycles that defined the character of the world. The mantle, that vast layer of rock between the crust and the core, was much hotter and more mobile than it is today. Convection currents rose and fell through it with greater intensity, transporting heat upward, driving volcanic activity and recycling materials between the surface and the deep earth. The crust, where it existed at all, was thin and fragile by comparison. It hadn't yet thickened into stable land masses, and what solid surface there was often cracked under pressure or melted back into the mantle. This resulted in a planet with a fractured, unstable surface, a patchwork of volcanic islands, unstable continental fragments, and vast areas of open ocean. Lava flows were common, forming new crust that might last a few million years before being subducted or melted again. Entire regions could rise from the sea, cool and stabilize, then disappear beneath the waves, only to be replaced by new volcanic zones elsewhere. It wasn't a tidy process, and it certainly wasn't predictable. It was molten, moody, and absolutely relentless. Much of this activity happened at mid-ocean ridges and hotspots, places where magma welled up from below to create new crust. Some of these features may have resembled modern equivalents like the Mid-Atlantic Ridge or the Hawaiian hotspot, but on a scale that was more active, more frequent, and possibly more intense. Without the thick plates and well-defined boundaries of today's tectonic system, these upwellings created crustal patches that moved irregularly, collided unpredictably, and sometimes sank back into the mantle before gaining any real stability. Volcanoes weren't just isolated cones dotting the landscape. In many areas, entire regions were volcanic, massive flood basalts, rift zones, chains of submarine eruptions that built temporary islands. The eruptions themselves varied from slow, oozing lava flows to explosive, gas-charged events that released ash and gases into the thick atmosphere. These eruptions helped shape the chemistry of both air and ocean, contributing gases like carbon dioxide, sulfur dioxide, and water vapor, as well as trace elements like chlorine and fluorine that would participate in further reactions at the surface. On land, where land existed at all, the results were temporary. Basaltic plains formed, eroded, and reformed, rock cooled slowly under the thick atmosphere, and chemical weathering was limited by the absence of any vegetation. Without roots to break apart rocks or soil to absorb water, the landscape was sculpted almost entirely by rain, tides, and gravity. Slopes collapsed, lava hardened and then cracked again. It was a dynamic, temporary, and fundamentally unstable surface, one that rarely lasted long enough to become truly permanent. Even underwater, the planet's volcanic mood was evident everywhere. Hydrothermal vent systems dotted the seafloor, especially near spreading centers. These were places where seawater percolated down through hot rock, became superheated, and then rose back into the ocean, carrying dissolved minerals and chemicals with it. Around these vents, life flourished, not photosynthetic life that depends on sunlight, but chemosynthetic microbes that harness chemical energy from reduced compounds like hydrogen sulfide to build organic molecules. These vent communities may have been among the most stable biological systems on the planet at the time. The surface was unstable, UV-bathed, and subject to constant change, but deep underwater, near a steady heat source, microbes could thrive. The energy flow from the mantle through these volcanic systems may have made life not only possible but genuinely sustainable. Volcanic islands, when they did rise above the ocean, created new and unique environments. Their surfaces cooled quickly, but their interiors retained heat for long periods. Rainwater falling on fresh basalt reacted with minerals, initiating weathering processes that would become increasingly important over time. Erosion carried material back to the sea, enriching the surrounding waters with nutrients and altering local chemistry in subtle but significant ways. These islands were temporary features, but while they lasted, they added variety to an otherwise monotonous surface. High points, ridges, slopes, and basins that didn't exist in the open ocean. Sometimes these islands collided with other crustal fragments, forming larger landmasses. These collisions often triggered even more volcanism, as magma intruded into existing rock, creating new mineral combinations and heating the crust from below. These processes were part of the early continental growth cycle, a repeating pattern of eruption, thickening, metamorphism, and stabilization that would eventually lead to the formation of stable continents. In places where volcanic arcs formed, similar to modern island chains like Japan or the Aleutians, repeated subduction and magmatism built up significant crustal thickness. These arcs may have been among the first long-lived land regions on Earth. Their structure, formed by oceanic crust diving beneath other oceanic crust, creating the kind of repeating volcanic systems that could accumulate material over truly long periods. And yet, none of this was permanent in any meaningful sense. Subduction often recycled crust back into the mantle before it could achieve real stability. Whole volcanic provinces may have formed, grown to substantial size, and then vanished completely in less than 100 million years. The Archean Earth was a system still trying to find some kind of equilibrium. The processes that governed it, volcanism, tectonics, erosion, were familiar in principle but radically different in scale, temperature, and timing from what we see today. Geologically, the evidence for all this volcanic activity comes not just from volcanic rocks themselves, but from the metamorphic zones around them. High-grade metamorphism, where rocks are buried and altered by intense heat and pressure, is extremely common in Archean terrains. It shows that volcanic regions were not only active but also deeply affected by crustal thickening and tectonic stacking, events that produced rock textures and mineral assemblages that point directly to a hot, dynamic, and constantly evolving surface. Even today, Archean volcanic rocks are among the most intensively studied formations for their mineral potential. The processes that built them often concentrated valuable elements, gold, nickel, copper, in ways that modern mining operations still pursue. These economic interests drive much of the detailed research into Archean geology, helping to map out the structure of rocks that have survived billions of years of weathering and tectonic distortion. Even beyond their economic value, these volcanic systems tell us something fundamental about the early Earth, that the surface we walk on now, so seemingly solid and settled, was once fluid, fiery, and under constant construction. Volcanoes weren't just a feature of the landscape, they were the architects. They helped build the first continents, contributed essential gases to the early atmosphere, sustained the first ecosystems, and participated in global cycles that would eventually lead to a planet with stable climates, protective ozone layers, and breathable air. And all of that began here, not in silence but in eruption, in the roar of heat meeting rock, gas meeting ocean, and chemistry meeting the earliest experiments in biology. As the volcanic surface kept shifting and changing, the life around it adapted with remarkable flexibility. Microbes colonized new lava flows, grew in sediments formed from volcanic ash, and found ecological niches near vents and hot springs. The Earth's surface was dangerous by any modern standard, but it was also incredibly rich in the raw materials of life. Each eruption, each new flow of basalt or komatiite, brought more material into the global cycle, more rock to weather, more nutrients to transport, more heat to harness for biological processes, and gradually, in the margins between land and sea, something else began to take shape. Not just microbial mats or chemical signatures, but physical structures, traces that would last long enough to become part of the geological record. Evidence that life wasn't just surviving in this harsh world, it was starting to build, to organize, to leave its mark. And once life starts leaving marks in stone, it becomes part of the geology itself, not just a passenger along for the ride, but an active participant in shaping the planet. The Earth we know today has a distinct and familiar palette: blue skies, white clouds, green forests, deep navy oceans. It's comforting, expected, even reassuring in its predictability. But during the Archean Eon, the color scheme was something else entirely, a world painted in hues we rarely see today. The skies were not blue. The seas were not the clear, sparkling blue-green we associate with healthy oceans. The world had not yet settled into its modern aesthetic, and if you could have stood on an Archean shoreline, assuming you could survive the atmosphere and radiation, what you would have seen around you might not resemble anything we readily associate with Earth today. Let's start with the oceans. Since they covered most of the planet's surface by this time, the seas were vast, persistent, and chemically active, but they were definitely not the sparkling blue expanses we picture when we think of water. The absence of oxygen in both the air and the water changed everything about their appearance. In the modern ocean, oxygen interacts with iron to bind it into insoluble forms that sink to the bottom, leaving the water relatively clear and blue. In the Archean, that process hadn't begun yet. Without free oxygen, iron remained dissolved in the ocean in extraordinarily high concentrations, and this gave the water a completely different appearance, likely green, possibly even brownish in some regions, depending on the specific mix of metals and suspended sediments. Iron-rich water has a distinctly greenish tint, especially when combined with other dissolved minerals. In areas near hydrothermal vents or active volcanic islands, the color may have deepened even further due to additional inputs like sulfur compounds or silica-rich fluids. Photosynthetic organisms had already emerged by this time, including early cyanobacteria, but they had not yet transformed the global chemistry of the planet. Their oxygen, produced through the remarkable process of photosynthesis, was still being absorbed by the oceans themselves and by iron-rich rocks on the seafloor. Until those chemical sinks were completely saturated, the oxygen stayed locked away and the ocean remained anoxic, a term meaning without oxygen that defines not just the biology, but the entire chemical environment. This lack of oxygen allowed for the persistence of other compounds that are extremely short-lived in today's oceans. Hydrogen sulfide, for example, may have accumulated in certain areas, especially in deeper or poorly mixed waters. Combined with dissolved iron, this could create distinct layers of chemically different water, a condition known as stratification. Surface waters stirred by wind and penetrated by sunlight may have had a different chemistry entirely than deeper regions fed by hydrothermal activity and the slow decay of organic sediments. These layers would have affected not only the color of the ocean but also its biological potential. Life in the surface layer would have needed to cope with UV radiation and low oxygen concentrations. Life in deeper waters would have faced high pressure, minimal light, and possibly toxic concentrations of sulfides. The result was a complex patchwork of environments, some relatively welcoming to life, others downright hostile, but all interconnected through ocean circulation and chemical exchange. Above this alien ocean, the sky wasn't the deep blue we associate with a clean, oxygen-rich atmosphere. That familiar color comes from the way nitrogen and oxygen molecules scatter sunlight, specifically blue wavelengths, through a process known as Rayleigh scattering. But in the Archean, the atmospheric composition was fundamentally different. There was nitrogen, yes, but little to no oxygen. The atmosphere was denser overall, loaded with gases from volcanic outgassing, carbon dioxide, methane, water vapor, and possibly ammonia. Methane in particular has a strong effect on how sunlight passes through the atmosphere. In high concentrations, methane can create a haze not unlike what we see on Saturn's moon Titan today, a haze that scatters light very differently than our modern atmosphere. Instead of the familiar blue, the dominant scattering may have favored reddish, pinkish, or orange hues, especially during sunrise and sunset. Combined with a dimmer sun and possibly high-altitude clouds or sulfur-based aerosols from volcanic activity, the visual effect could have been quite dramatic. The term hazy applies here not just visually but chemically. The Archean sky was a reactive environment where sunlight striking methane could trigger photochemical reactions. These reactions would break methane apart and form more complex hydrocarbons, some of which would condense into airborne particles, thickening the haze even further. This photochemical smog would have filtered sunlight, changed the planet's albedo, and contributed to either warming or cooling depending on how thick it became at any given time. That atmospheric haze might actually have protected early life from deadly UV radiation, acting as a kind of crude but effective sunscreen. Without an ozone layer, which today is formed from the interaction between oxygen and UV light, the surface would have been exposed to dangerously high levels of ultraviolet radiation. Any shielding, even from organic haze, could have made the difference between life and death for surface-dwelling or shallow-water organisms. It's also quite possible that this methane haze fluctuated significantly over time. Changes in microbial activity, major tectonic events, or shifts in global temperature could alter both methane production and destruction, creating periods where the haze thickened dramatically or cleared almost entirely. Each shift would have affected not just how the sky looked, but how much sunlight reached the surface, with potential consequences for climate stability, ocean chemistry, and biological productivity. The interaction between the green ocean and the pinkish, hazy sky created a world of unusual and striking visual contrasts. Where today we have familiar color boundaries, blue sky meeting blue sea, green forests stretching toward gray mountains, the Archean offered something much less uniform and predictable. The sea was darker and more mysterious, the sky was softer or dustier, and the boundary between them may have been more diffuse, blurred by persistent haze and high humidity. The overall effect would have been alien but not necessarily unbeautiful, just utterly different from anything in our experience. In terms of temperature, the greenhouse gases in the atmosphere, mainly carbon dioxide and methane, were doing most of the heavy lifting to keep the planet warm. They trapped heat efficiently and kept surface temperatures within the range needed to maintain liquid water, even with a sun that was significantly dimmer than today's. But this was definitely not a finely tuned system running in perfect balance. Periods of intense volcanic activity, shifts in weathering rates, or even changes in biological activity could tip the scales dramatically. Cooling events may have occurred, possibly even glaciation in limited regions, though evidence for global freezing during the Archean remains hotly debated among scientists. The point is that the climate was not fully stable or predictable. It was still in development, adjusting and readjusting as the planet's interior cooled, as the crust matured, and as life began to interact more deeply and meaningfully with its chemical environment. The color of the ocean, the chemistry of the air, the texture and appearance of the clouds, all of it was connected in complex feedback loops. Each component influenced the others, sometimes subtly over long time periods, sometimes quite profoundly during periods of rapid change. Life at this stage was still entirely microscopic, moving through this colorful but alien world in thin films, in suspended mats, in planktonic drifts across shallow basins and tide pools. It didn't need clear skies or clean blue water to thrive. It needed energy, raw materials, and time to adapt. and it found those necessities in the boundary zones, near hydrothermal vents, in sunlit tidal flats around the shores of volcanic islands. Wherever gradients formed and resources moved through the system, life was there, adapting to conditions and slowly shaping them in return. And though we can't see this ancient world directly, we do have the rocks as witnesses. Banded iron formations, which formed when the first traces of oxygen from photosynthetic microbes reacted with dissolved iron in the ocean, give us the chemical signature of a green sea slowly turning towards something new. Sulfur isotope records show us that the atmosphere was still anoxic but beginning to change in measurable ways. Carbon isotope data hints at biological productivity increasing in certain regions, perhaps seasonally, perhaps more continuously. These indirect but reliable records allow us to reconstruct a picture of the Archean world, not with sharp detail, but with enough consistency to imagine it clearly. A world where the air carried methane instead of oxygen, where the water carried iron instead of marine life as we know it, and where light filtered through a dusty reactive sky to illuminate an alien but functioning planet. A world that wasn't barren or dead, just utterly unfamiliar by our standards. A working system, not yet refined but already showing the potential for something greater. And within those strange conditions, biology was not just surviving, it was beginning to leave patterns in the rock record. Not fossils, not yet, but influence and chemical change that would accumulate over deep time. Those changes would grow more pronounced as photosynthetic microbes continued to populate shallow seas and mat-like communities began to stabilize in sedimentary environments. The haze in the sky would start to fade as oxygen slowly rose. The water would gradually change color as iron was pulled out of solution. The entire world, still raw and unstable, would respond to the growing influence of life, not overnight, not dramatically, but persistently and irreversibly. And eventually, in certain special places, life would begin to build something genuinely physical, not just molecules and metabolic pathways, but structures, traces, stacks of sediment bound together by biology, recording its presence in the most durable material Earth has to offer, stone. These would be among the first features to survive into the fossil record, visible even billions of years later as testament to life's growing influence. The colorful, alien ocean and sky had set the stage perfectly. Now life was ready to step more boldly into view. The idea of a cradle suggests something gentle, something protected, something inherently safe. But the Archean Earth didn't offer safety in any conventional sense we'd recognize. The surface was unstable, the air was unbreathable, the sunlight was harsh and often deadly. Yet somewhere in that unstable, hostile world, life not only began, it endured, adapted, and thrived. It found energy where it could, built structure from available materials, made copies of itself, and gradually adapted to an environment that was anything but welcoming. The conditions were not ideal by any stretch of the imagination. They were not stable, predictable, or comfortable, but they were sufficient, just enough for something remarkable to take hold and refuse to let go. Pinpointing exactly when life began is probably impossible, and may always remain so. The fossil record doesn't extend back far enough to capture the earliest stages, and biology at its most fundamental level leaves behind very few direct traces when it exists only as single-celled organisms drifting in the vast sea. But the chemical signatures preserved in certain ancient rocks strongly suggest that by the mid to late Archean, over 3.5 billion years ago, life was already widespread in the oceans, already engaged in photosynthesis in some regions, and already participating actively in the global cycling of carbon, nitrogen, and sulfur. The earliest life forms weren't made of cells in the way we think of them today. Biology probably began as much simpler, self-replicating systems, molecules that could copy themselves, surrounded by membranes formed from naturally assembling lipids and other organic compounds. These structures weren't alive in the full biological sense we understand today, but they performed the absolutely necessary functions. They grew, they divided, they competed for resources, Over vast stretches of time, through mutation and natural selection, these proto-life forms became increasingly complex, eventually developing the first true cellular structures and sophisticated metabolisms. The source of energy for these early systems depended entirely on their location and circumstances. In deep-sea environments, hydrothermal vents offered powerful chemical gradients. Differences in temperature and chemical composition between the vent fluids and the surrounding water. These gradients could drive the synthesis of organic molecules and provide the steady energy needed for metabolic reactions. In shallower waters, sunlight gradually became a viable energy source, used first by organisms that didn't require oxygen and later by those that began to produce it as a byproduct. Chemosynthesis almost certainly came first. The remarkable ability to convert inorganic molecules like hydrogen sulfide or methane into usable energy and biomass. Microbes living near hydrothermal vents still do exactly this today, thriving in environments that would be instantly lethal to most other forms of life. They don't need sunlight at all. They rely instead on specialized enzymes that strip electrons from one molecule and transfer them to another, releasing energy in the process that can be used to power all the basic functions of life. This kind of metabolism could operate in total darkness, in the high-pressure, mineral-rich environments of the deep ocean floor. Photosynthesis came later, though exactly how much later remains a subject of ongoing scientific debate. Some of the earliest known signs of photosynthetic activity appear in rocks dated to around 3.5 billion years ago, but the process may have begun even earlier. This early form of photosynthesis almost certainly did not produce oxygen as we know it. Instead, it may have used hydrogen sulfide or other reduced compounds as the electron donor, releasing sulfur or other elements rather than the oxygen that would later transform the planet. Only later, with the evolution of cyanobacteria, did oxygenic photosynthesis begin, the revolutionary process that splits water molecules and releases oxygen as a byproduct. That development, though slow to take effect, would eventually change everything about our world. But at first, the oxygen produced didn't accumulate in the atmosphere at all. It reacted immediately and completely with iron dissolved in the oceans, forming insoluble iron oxides that settled to the seafloor like a slow, steady rain. Over millions and millions of years, this process created the spectacular banded iron formations, alternating layers of iron-rich and iron-poor rock that still appear in ancient geological terrains around the world. These rocks represent some of the earliest large-scale biological signatures on Earth, formed not from fossils of organisms themselves, but from the chemistry driven by life. Where exactly did life begin? There are several compelling candidates, each with its own advantages and challenges. Deep-sea hydrothermal vents offer one particularly attractive possibility: hot, mineral-rich environments where water and rock interact constantly, creating gradients and providing a steady flow of nutrients and chemical energy. Alkaline vents, in particular, provide natural proton gradients across porous rock membranes, structures remarkably similar to the ones cells use today to generate energy. It's an elegant hypothesis that connects modern biochemistry directly to ancient geological processes. Shallow water environments offer another intriguing possibility. Tide pools and coastal flats could provide the wet-dry cycles that might concentrate organic molecules through evaporation and bring them into contact with mineral surfaces that could catalyze important reactions. The exposure to sunlight and other environmental stresses could have driven rapid evolution, favoring increasingly robust molecular systems capable of surviving harsh conditions. There's also the fascinating idea of life beginning in the subsurface, in the pores and cracks of hot rock, insulated from the dangerous surface environment, but still connected to chemical flows and energy sources. This underground environment would offer protection from UV radiation and impact events while still allowing interaction with water, heat, and the diverse minerals that could catalyze the formation of complex organic molecules. It's entirely possible that life began in one of these environments and then migrated to others as conditions changed and new opportunities arose. Regardless of its exact origin, by the late Archean, life had clearly spread far beyond its birthplace. It occupied a remarkable variety of ecological niches, hydrothermal vents, tidal flats, shallow seas, and probably many environments we haven't yet imagined. Microbes grew in dense mats on submerged surfaces, forming layered communities that trapped sediments and created complex chemical microenvironments. These mats weren't just passive films of biology, they actively altered the pH of the water around them, changed the oxidation-reduction conditions in their immediate vicinity, and influenced the deposition and transformation of minerals. In some particularly favorable locations, these microbial mats became stable enough to build substantial physical structures. As the organisms trapped and bound sediment particles layer by layer, they formed domes, columns, and other distinctive shapes. Over time, these biological constructions grew into stromatolites, laminated structures that preserve the pattern of microbial growth and sediment accumulation across thousands of years. Some of the oldest known stromatolites date to over 3.4 billion years ago, and they appear in rock formations that were once shallow marine environments. Stromatolites represent some of the first visible evidence of life actively shaping its environment in a structured, organized way. They show us that life wasn't just present during the Archean, it was active, building, modifying its surroundings, and persisting through environmental changes that would have destroyed any individual organism. These weren't isolated, one-off events either. Stromatolites appear in multiple locations across different parts of the ancient world, suggesting that wherever conditions were suitable, life found a way to establish a foothold and maintain it over geological timescales. The biological processes behind these remarkable structures also began to influence the planet more broadly and systematically. Photosynthesis, whether oxygenic or not, gradually altered the balance of gases in the ocean. Metabolism affected the chemistry of sediments in measurable ways. Life was beginning to participate in planetary feedback loops, taking in materials from the environment, processing them through biological pathways, and returning them in different chemical forms. The carbon cycle, the nitrogen cycle, the sulfur cycle, all of these fundamental planetary processes began to take recognizable shape during the Archean, even if they weren't yet fully developed or stable. There's no sharp dividing line between non-life and life, just as there's no clear boundary between simple chemistry and complex metabolism. But somewhere during this eon, the crucial shift occurred. Molecules became systems. Systems became organisms, and organisms began to persist across generations, adapt to their changing surroundings, and influence the environment around them in increasingly significant ways. The Earth was no longer just a physical and chemical system governed by geology and atmospheric physics. It had become, however quietly and gradually, a biological planet as well. That transition didn't end the chaos or make the world suddenly peaceful and stable. The planet was still volcanically active, tectonically restless, and chemically dynamic. The sky was still thick and strange, the ocean still alien by our standards. But now there was something genuinely new in the system: persistence. Life that could survive major environmental changes, or at least return and rebuild afterward. Communities that could regrow after disturbance, adapting and evolving in response to new challenges. Chemistry that could repeat itself, refine itself, and become more efficient with time and experience. And over the vast stretches of geological time, those biological systems would begin to expand their influence dramatically. Life would move from isolated mats to larger, more complex communities. It would begin to influence the shape of coastlines, the composition of oceans, and eventually the very nature of the air above. Its fingerprints, still faint but increasingly detectable, were beginning to show up everywhere, not in bones or leaves or any of the familiar fossils we associate with life, but in isotope ratios, mineral textures, organic carbon compounds locked into sedimentary rocks. The cradle of life, such as it was, definitely didn't rock gently or provide easy comfort. It was surrounded by fire, toxic gas, and shifting tides that could expose organisms to deadly radiation, but it held together long enough for life to establish itself. And as it did, it set the stage for everything that would follow. Not with certainty or speed, but with the kind of resilience that comes from being tested constantly and surviving. The resilience to persist through everything the Earth could throw at it. Volcanic eruptions, atmospheric changes, crustal movements, chemical upheavals. That resilience would prove to be more than enough, because in the long story of this planet, persistence always matters more than speed or perfection. From this foundation, life wouldn't stay small and simple forever. It would begin to change the very rocks it grew on and in, not just chemically, but in ways that would be visible billions of years later. And it would do all of this in a world still very much in flux, a world where oceans rose and fell, where land shifted underfoot, and where biology was just beginning to discover its power to reshape geology itself. By the time microbial life had carved out its foothold in the Archean world, the planet offered no shortage of places for organisms to grow and evolve. But very few of those environments would seem even remotely welcoming by the standards we're used to today. The oceans were dark and murky in some regions, chemically unstable in others, and often stratified into distinct layers that varied dramatically in temperature, salinity, and toxicity. The air above was still completely devoid of oxygen, filled instead with volcanic gases and subjected to occasional bursts of ultraviolet radiation from a sun that was filtered only by organic haze and clouds. And yet, incredibly, microbes didn't just survive in this environment. They thrived, diversified, and began to transform their world. They didn't need clear, blue water or clean air to flourish. They needed energy, raw materials, and time, and the Archean provided all of these in abundance. The majority of microbial life during this period was prokaryotic, simple, single-celled organisms without a nucleus or other membrane-bound organelles. These represented the earliest domains of life, bacteria and archaea. Both had evolved remarkable adaptations that allowed them to survive in what we would consider extremely harsh conditions. Some preferred intense heat, others thrived in highly saline environments, and still others flourished in acidic pools or near vents loaded with metals and sulfur compounds. They were incredibly flexible, not necessarily in their physical forms but in their metabolic pathways, and that metabolic flexibility made them extraordinarily resilient to environmental change. The murkiness of the Archean world wasn't just a visual characteristic, it was fundamentally chemical. The oceans were absolutely saturated with dissolved metals, especially iron, which in its reduced form remained completely soluble in the anoxic water. Hydrogen sulfide, methane and ammonia were all present in varying concentrations depending on the region and depth. In this chemically complex environment, microbes became highly specialized metabolic engineers. Some oxidized sulfur compounds for energy, others reduced nitrates or sulfates. Some fed directly off hydrogen gas released from geological processes. These diverse metabolic pathways became the scaffolding of the early biosphere, invisible to the naked eye, but absolutely essential for the functioning of life on Earth. Microbes didn't simply float aimlessly through the water column either. Many formed dense, organized communities, clinging to mineral surfaces or growing as extensive mats across submerged rocks and sediments. These microbial mats were structurally simple but biologically extraordinarily diverse. Layer upon layer of different microorganisms created complex microenvironments within the mat structure. Thin zones where gradients of light, temperature, oxygen, or nutrients allowed different species to coexist, and even cooperate. In the uppermost layers, photosynthetic organisms captured energy directly from sunlight. Beneath them, anaerobic microbes fed on the waste products and organic compounds produced by the photosynthesizers, creating self-sustaining ecosystems that required no external inputs except light and basic chemical elements. Some of these microbial mats left physical traces that we can still study today, stromatolites, but the vast majority did not. Most microbial life existed and evolved without ever leaving a direct imprint in the rock record. Its legacy is recorded instead in subtle but detectable chemical signatures, isotope ratios, mineral textures, organic carbon compounds locked into sedimentary layers. These signals are often faint and require sophisticated analytical techniques to detect, but they are remarkably consistent across different locations and time periods. They tell us that by the mid-Archean, microbial life was not just present but geographically widespread, adapted to an impressive variety of environments, and capable of surviving major disruptions to the planetary system. Photosynthesis, even in its early non-oxygen producing forms, gave microbes a significant evolutionary advantage. Light was an abundant and reliable energy source, even when filtered through the dusty, hazy atmosphere of the early Earth. Anoxygenic photosynthesizers could use sulfur compounds or iron instead of water as their electron source, producing elemental sulfur or ferric iron rather than the oxygen that would later transform the planet. These organisms could thrive in shallow water environments, particularly around volcanic shores where chemical inputs were steady and light could penetrate to the seafloor. Their metabolic activity changed local chemistry in measurable ways, affecting pH levels, redox balance, and the solubility of various minerals in their immediate environment. Oxygenic photosynthesis, the kind that splits water molecules to release oxygen, emerged sometime during the Archean, almost certainly among cyanobacteria. This biochemical innovation did not create a breathable world overnight, or even over millions of years. For an extraordinarily long time, the oxygen these organisms produced was immediately absorbed by dissolved iron and organic matter in the ocean, preventing it from accumulating in the atmosphere. But the process marked a crucial turning point in Earth's history. It introduced a completely new chemical pathway, with truly global implications for the future evolution of life and the planet. In the murky, iron-rich waters of the Archean Ocean, cyanobacteria began to alter their surroundings in increasingly permanent ways. As they grew in large colonies, their photosynthetic byproducts interacted directly with the surrounding water and seafloor, forming mineral precipitates and altering the chemistry of entire basins. They played a central role in the formation of banded iron formations, thick, distinctive layers of iron-rich rock that settled out of the ocean when oxygen produced by photosynthesis bound with dissolved iron and rendered it insoluble. These bands, alternating between iron oxides and other sedimentary layers, represent some of the most durable evidence we have for early biological activity. They demonstrate that microbial metabolism wasn't confined to isolated pockets or restricted to certain seasons. It was happening on a scale large enough to affect entire ocean basins repeatedly over millions of years. And while banded iron formations don't preserve the microbes themselves, they clearly record the consequences of large-scale microbial activity. Biological processes leaving behind unmistakable geological artifacts that we can still study today. Elsewhere in the ocean system, microbial communities adapted to radically different conditions. In deeper waters, chemosynthetic bacteria fed off the unique chemistry of hydrothermal vent systems, oxidizing hydrogen sulfide or methane and fixing carbon dioxide into organic matter without any need for sunlight. These communities likely formed the earliest recognizable analogues to complete ecosystems, with producers, consumers, recyclers, and waste management systems all operating at the microscopic level through purely chemical pathways. Archaea, though similar to bacteria in their basic structure, were particularly well suited to extreme environments that would be lethal to most other forms of life. Some lived in extremely high-temperature regions around volcanic vents. Others could tolerate extraordinary salinity or acidity levels that would destroy other organisms. They developed unique metabolic strategies, including methanogenesis, the production of methane from carbon dioxide and hydrogen. This process, still active in certain environments today, contributed significantly to the buildup of methane in the early atmosphere, reinforcing the greenhouse effect and helping maintain Earth's surface temperature despite the relatively dim sun. The complex interplay between microbial life and the surrounding environment was constant and dynamic. Microbes altered their chemical surroundings, which in turn influenced their own evolution and the evolution of other organisms. Minerals precipitated differently around microbial mats, creating unique textures and compositions. Sediments accumulated at different rates depending on the level and type of microbial activity in a given area. In some regions, life became the dominant force shaping surface chemistry, even though it remained invisible to any hypothetical observer. Despite all this remarkable activity, there was still no oxygen in the atmosphere, no multicellular organisms of any kind, and no food webs in the modern sense. Life was quiet, microscopic, and relatively limited in its external impact on the physical landscape. But it was steadily laying the groundwork for everything that would come later. Every microbe that fixed carbon, oxidized sulfur, or produced methane was participating in a much larger system, a planetary engine slowly but surely converting raw chemical energy into biological complexity. The murkiness of the Archean wasn't just a visual characteristic, it was conceptual. The boundaries between geology, chemistry, and biology were still fluid and interconnected. Rocks provided habitat for life. Life actively changed chemical conditions. Chemistry altered the formation and transformation of rocks. It was a world where physical and biological processes were thoroughly intertwined, difficult to separate and deeply dependent on one another. Over time, as microbial life continued to spread and diversify, its effects on the planetary system would become harder and harder to ignore. Oxygen would begin to accumulate first in shallow waters, then gradually in the atmosphere itself. Microbial communities would start to leave more permanent and visible traces in the rock record. The surface of the Earth would begin to reflect the growing presence and influence of life, not just as a thin film on top of the rocks, but as an active process operating within the crust, within the ocean, and eventually within the air itself. But even in this early phase of biological evolution, the dominance of microbes cannot be overstated. For billions of years, literally half the age of the planet, they were the only form of life on Earth. They filled every available ecological niche, evolved rapidly in response to environmental changes, and shaped the chemistry of the planet in ways that still persist today. Their legacy is not just historical or academic, it is foundational to everything that came after. And as they grew, divided and adapted in the murky waters of the Archean, they brought the Earth steadily closer to a major transition, one that would not happen quickly or dramatically, but one that would eventually change everything about our world. The quiet, persistent work of microbes layered over deep geological time would eventually shift the composition of the atmosphere itself, paving the way for a world with air that could be breathed, skies that could turn blue, and life that could finally grow beyond the scale of a single cell. In a world where almost nothing stayed in one place for very long, stromatolites were remarkable for their persistence. They grew wherever conditions allowed and remained standing where little else could survive. They didn't look like much. Not then, certainly not now to the casual observer. Mounds, domes, sometimes flattened sheets of layered rock, to the untrained eye, they might appear to be just another geological formation, but they were so much more than that. They were living architecture, built through the slow, repetitive work of microbial communities, laying down layer after layer of life and sediment, season after season, year after year. And they were everywhere the conditions were right. Stromatolites weren't the first form of life on Earth, but they were definitely the first to leave a visible structural mark on the landscape. Unlike the subtle chemical traces left behind in isotope ratios or the microbial mats that decomposed without leaving physical evidence, stromatolites persisted through time. They preserved not just the presence of life, but the actual shape and structure of the life that built them. In doing so, they preserved time itself, not just a moment or an event, but an entire process, a repeated rhythm of growth and burial, that continued over years, centuries, and millennia. The organisms primarily responsible for these remarkable structures were cyanobacteria, single-celled photosynthetic microbes with the ability to bind sediment grains and trap them within thin, sticky biological layers. These bacteria lived in dense mats, packed together in thin films that covered shallow seafloors and tidal flats. During daylight hours, they captured sunlight and converted carbon dioxide into organic matter through photosynthesis. At night, they rested or processed the materials they had gathered during the day. Over time, as sediment naturally settled on top of the growing mats, the bacteria would migrate upward toward the light, rebuilding their position at the surface. When new sediment fell, the microbes would rise again, always seeking the optimal position for photosynthesis. Each cycle added a new layer to the growing structure, thin but distinct, visible today as fine laminations that record the passage of time with remarkable precision. The layering process wasn't purely biological, though. It involved complex interactions between life and the physical environment. Sediment supply, water chemistry, ocean currents, and microbial metabolism all played important roles in determining the final shape and structure of each stromatolite. The result was a formation that was both shaped by its surroundings and remarkably resistant to environmental change. Stromatolites could survive and continue growing in places where other forms of life simply could not persist, partly because their mat-like communities provided mutual protection. The outer layers of bacteria shielded the interior organisms from deadly UV radiation, desiccation during low tides, and sudden chemical changes in the water. As they grew larger, stromatolites also altered the microenvironment around them, creating chemical gradients and flow patterns that could benefit the organisms living within and nearby. Some stromatolites formed in calm, shallow marine environments, where water depth varied only slightly and sunlight was abundant throughout the growing season. Others developed in more turbulent settings, where waves and tides were constantly disturbing the surface and redistributing sediments. The shapes and sizes of stromatolites varied significantly with their environmental conditions. Tall, columnar forms developed in deeper water where competition for light was more intense. Flatter, more encrusting types grew in areas with stronger currents or higher rates of sedimentation where vertical growth would have been difficult to maintain. They were not isolated phenomena restricted to a few special locations. Archean stromatolites appear in numerous locations around the world, in Australia, South Africa, Canada, and many other regions where ancient rocks are well preserved. Their global distribution strongly suggests that wherever environmental conditions were suitable, these remarkable structures emerged independently. They weren't confined to a single habitat, climate zone, or geological event. They represented a successful biological strategy, a way for life to persist, protect itself, and create stable habitat in an otherwise unstable world. And that strategy clearly worked across vast distances and enormous spans of time. While the forms and structures of stromatolites are relatively simple compared to the complexity we see in later fossils, their presence marks a fundamental shift in the relationship between life and Earth's surface. Before stromatolites, life was mostly invisible, detectable only through subtle chemical signatures. After their appearance, life had begun to have a measurable physical impact on the landscape. The seafloor was no longer shaped only by ocean currents, tides, and sediment transport. It was also actively shaped by biology. Microbial life was no longer simply reacting to its surroundings and adapting to whatever conditions it encountered. It was building, constructing, modifying the environment to better suit its needs. In doing so, it began to change the world around it in increasingly significant ways. Photosynthesis, especially the kind carried out by cyanobacteria, produced oxygen as a waste product. At first, this oxygen reacted immediately with dissolved iron in the oceans, forming insoluble iron oxides that settled out of the water column and created the distinctive banded iron formations we can still study today. But over time, as these chemical sinks gradually filled up, more and more oxygen remained dissolved in the water and eventually began to escape into the atmosphere. Stromatolites played a central role in this slow but monumental transformation. As visible hubs of intensive microbial photosynthesis, they contributed significantly to the global oxygen budget. Not in a dramatic, explosive way. This definitely wasn't a revolution that happened overnight. It was a long, steady climb that took hundreds of millions of years to complete. But the oxygen produced by stromatolite building communities began to accumulate, first locally in the shallow marine waters immediately around the structures, then more broadly as photosynthesis became more widespread, and the global balance of atmospheric gases began to shift in a new direction. This shift wasn't smooth or predictable, however. Oxygen is an extremely reactive gas, and its gradual increase triggered cascading changes in ocean chemistry that sometimes destabilized entire ecosystems. Some anaerobic organisms, those that had evolved to live without oxygen and were actually poisoned by it, were pushed into more marginal environments. Others adapted by evolving new metabolic pathways, while still others simply died off when they couldn't cope with the changing conditions. Oxygen created both new opportunities and serious disruptions, forcing life to change, move, or disappear entirely from regions where it had previously thrived. But the stromatolites themselves remained remarkably persistent throughout much of the Archean. They were among the dominant visible forms of life in the shallow marine landscape, not just living in their environment but actively shaping it through their biological and physical processes. They altered water flow patterns around them, trapped and concentrated nutrients from the surrounding water, and created small-scale ecosystems within and around their layered structures. They functioned as both habitat and organism, environment and inhabitant combined in a single integrated system. They also began to change the sedimentary record in ways that we can still detect and study today. The laminated textures characteristic of stromatolites are distinctly different from purely physical sediment layers deposited by currents and waves. Their presence in ancient rocks marks environments where biology had a significant influence on sediment deposition, a record written in stone of life actively participating in geological processes. The fine layering within stromatolites often records daily, seasonal, and annual cycles in growth, influenced by changes in light availability, nutrient supply, and environmental conditions. Reading stromatolites is like reading a detailed diary written in stone, slow and repetitive perhaps, but remarkably rich in information about ancient environmental conditions and biological processes. Even the death and decay of stromatolites contributed to the future development of life on Earth. As stromatolite building mats died and decomposed, they released organic matter into the surrounding sediment. This material became food for other microbes, helped bind sediments together, and participated in chemical reactions that influenced the mineralogy and chemistry of the seafloor. In this way, even death and decay in the stromatolite world became part of an ongoing construction process, contributing to the slow but steady accumulation of organic-rich sediments that would later play important roles in global geochemical cycles. Today, modern stromatolites are quite rare, surviving only in isolated, hypersaline environments that are too extreme for most grazing organisms that would otherwise destroy the delicate microbial mats. But during the Archean, there were no grazers at all, no animals to disrupt the surface, no predators to consume the mats, no multicellular organisms of any kind. Microbes were free to build their layered structures without interference, and they did so on a scale that's almost impossible to imagine today. This period, when stromatolites were widespread and dominant features of shallow marine environments, represents one of the earliest and clearest examples of ecosystem engineering, life actively altering its environment in a sustained, large-scale way that benefited not just individual organisms but entire communities. The structures didn't grow quickly. Biological processes rarely do. They didn't spread rapidly across the landscape, but they endured for geological time periods that dwarf human experience, and over those vast spans of time, they laid crucial groundwork for all the complexity that would follow. They altered the chemistry of the ocean in measurable ways. They influenced atmospheric composition through their photosynthetic activity. They created environmental conditions in which other organisms, perhaps forms of life not yet even imagined, could eventually evolve and thrive. And they told a story that we can still read today, not through language or symbols, but through form and structure. A dome preserved on an ancient seafloor, a ripple pattern in billion-year-old sediment, a trace of biological organization where none had existed before. These weren't fossils of bodies in the traditional sense. They were fossils of behavior, the preserved record of repeated, persistent biological action, of life adapting and organizing and building over time, as Earth moved slowly but inexorably toward a more oxygen-rich future. Stromatolites were already an integral part of that transition, even though they had no plan or foresight about what they were creating. Their daily activity of photosynthesis and growth gradually created the conditions in which more dramatic changes could eventually unfold. The stage was still relatively small, the biological actors still microscopic, but the script of Earth's history was definitely starting to shift in a new direction. The biosphere, once hidden and detectable only through chemistry, was beginning to leave its mark not just in molecular signatures but in visible physical shape. And as the planet responded to these changes, slowly, gradually, but irreversibly, it opened the door for new forms of interaction between life and rock, life and light, life and the very air itself. What came next wouldn't happen immediately, but the trajectory was clearly set. Life had discovered how to build lasting structures, and eventually it would learn to build even more complex and influential ones. The oceans were teeming with life. The surface was bathed in sunlight, filtered though it was through alien skies. The atmosphere had weather patterns and chemical cycles. But what the Archean world didn't have, not yet, was breath, at least not the kind that moves air into lungs, draws oxygen into blood, and fuels the motion of muscles and minds. Breathing, in that sense, wasn't even on the table as a possibility. The world simply hadn't made the right kind of air for it yet. There was no shortage of gases in the Archean atmosphere. It was thick with carbon dioxide, heavy with water vapor, laced with methane and ammonia and sulfur compounds that painted the sky in unfamiliar hues. But oxygen, the molecule that defines modern respiration, metabolism, and ultimately consciousness itself, was barely present at all. Microbes had started to produce it through photosynthesis. Yes, but the Earth wasn't letting it accumulate freely, not yet. Every atom of oxygen released into the ocean was immediately seized by something else, most often iron dissolved in the water. The oceans were absolutely saturated with ferrous iron, dissolved and waiting. When oxygen encountered it, the reaction was fast and complete. Ferrous iron became ferric, precipitated out of solution, and settled to the bottom as rust-red minerals. The oxygen didn't linger in the water. It didn't accumulate in the air. It simply got used up over and over again. Even once much of the iron was tied up and settled into the rock record as those distinctive banded iron formations, other chemical sinks remained active. Volcanic gases readily absorbed free oxygen. Organic matter soaked it up during decay processes. Sulfur compounds were oxidized wherever they encountered this reactive new molecule. The chemistry of the early Earth was fundamentally built around oxygen's reactivity, its tendency to bond with almost everything it touched. And for billions of years that meant it was rarely allowed to stick around long enough to accumulate in any meaningful concentrations. So for the vast majority of Earth's early history, life got by perfectly well without oxygen. Anaerobic metabolisms, those that don't require oxygen, dominated completely. Microbes used fermentation pathways, or relied on chemical reactions involving sulfur, nitrogen, or hydrogen for their energy needs. Some used light for photosynthesis, but not the kind that splits water molecules to make oxygen. Others fed on chemical compounds leaking from the seafloor or released by volcanic eruptions. The range of metabolic strategies available to early life was remarkably wide, and most of them didn't just work without oxygen, they actually depended on its absence. Respiration as we understand it today hadn't evolved because it simply couldn't. You don't build a complex oxygen-handling biochemical system in a world that offers essentially no oxygen to work with. And without oxygen readily available in the environment, there was no evolutionary pressure or incentive to develop ways to extract energy from it. Other metabolic pathways worked well enough, especially for small single-celled organisms with relatively simple energy requirements. There was no immediate pressure to develop something more efficient or complex. But that situation was beginning to change, slowly and almost imperceptibly. Microbes like cyanobacteria were releasing oxygen into their immediate environment through photosynthesis, and some of that oxygen was starting to stick around in tiny pockets, within microbial mats, in thin water layers near the surface, in microenvironments where local chemistry had shifted just enough to allow oxygen to persist. These regions became tiny oases of oxidation, chemically distinct from the vast anoxic world around them. They were small and often temporary, but they were persistent enough to create new kinds of environmental pressures. In these microenvironments, oxygen could actually be toxic to organisms that weren't prepared for it. This highly reactive molecule could damage proteins, disrupt cell membranes, and interfere with metabolic reactions that had evolved in its complete absence. Microbes that had thrived for millions of generations suddenly found themselves needing to cope with what was essentially a new form of pollution. Some organisms simply avoided oxygen-rich areas when possible. Others evolved defensive mechanisms, antioxidant systems, and repair enzymes that could neutralize reactive oxygen species. And a few remarkable lineages found ways to turn this liability into an asset, learning to use oxygen for their own metabolic purposes. The evolutionary step from oxygen tolerance to oxygen utilization was gradual, but once it began, the payoff was enormous. Aerobic respiration, the process of extracting energy from organic molecules using oxygen as the final electron acceptor, is far more efficient than any anaerobic pathway. It yields vastly more energy per molecule of food consumed, allowing organisms to grow faster, move more actively, or build more complex cellular structures. But in the Archean, that evolutionary potential was still mostly unrealized. The environment simply wasn't ready. Oxygen wasn't available in high enough concentrations to make aerobic respiration a viable strategy for most organisms. Even so, traces of adaptation to oxygen were beginning to appear in the biochemical toolkit of early life. Some microbes developed enzymes specifically designed to neutralize reactive oxygen species, molecules that form when oxygen reacts partially with other cellular components. These protective systems, originally evolved as defensive mechanisms, could over time be modified and repurposed as tools for actually using oxygen intentionally. But that evolutionary leap wasn't forced or urgent during the Archean. Oxygen was still scarce overall, anaerobic life still dominated most environments, and there was no immediate crisis driving rapid change. The air itself clearly reflected this biological reality. It wouldn't support combustion of any kind. You couldn't start a fire even if you had fuel and a spark. There were no flames anywhere on the planet, no oxidative weathering processes on land, no rust formation on exposed rocks. Materials exposed at the surface were altered by water and physical erosion, but not by reaction with atmospheric oxygen. Soils didn't form the way they do today, with iron oxides giving them their characteristic colors. There were no forests to burn, of course, but more fundamentally, there was no air capable of supporting combustion in the first place. The absence of atmospheric oxygen meant the absence of an entire category of chemical and physical processes that we take for granted today. No aerobic decomposition of organic matter, no large-scale ozone layer forming in the upper atmosphere, no visible signs of respiration anywhere on the planet's surface. The Earth was certainly active and definitely alive, but it was quiet in a way that's almost impossible for us to imagine. No wind whistling through leaves. There were no leaves, no sounds of breathing or heartbeats. Nothing had lungs or hearts yet, just chemical cycling, microbial metabolism, and a sky tinted pink or orange depending on the atmospheric methane concentration. We tend to think of breathing as such a basic, fundamental function, something essential and elemental to life itself. But on the scale of Earth's entire history, respiratory metabolism is actually a relatively late arrival, an adaptation to a dramatically changed world, rather than a starting point for biological evolution. For most of our planet's existence, literally billions of years, or about half the age of the Earth, respiration was entirely microbial, completely anaerobic and relatively slow by modern standards. Breathing in the sense we understand it wasn't missing from the Archean world. It simply wasn't needed yet. And yet, all the seeds of future change were already present and growing. The microbes photosynthesizing in shallow seas, the microbial mats building stromatolites, the occasional bursts of oxygen production in small pockets of water. All of this biological activity was slowly but steadily preparing the ground for something completely unprecedented. The chemical sinks that had been absorbing oxygen for so long were gradually filling up. The sources of oxygen production were becoming more numerous and more active, and the delicate balance that had kept oxygen levels near zero was starting to shift, almost imperceptibly, towards something genuinely new. No one would have noticed these changes at the time. There were no lungs to detect differences in air quality, no minds capable of perceiving environmental trends, but the planetary chemistry was definitely moving in a new direction. The Earth was heading towards something unfamiliar and unprecedented, not because of a single dramatic event, but because of a critical threshold that once crossed could never be undone. Breathing hadn't been invented yet, but the world was slowly, patiently building the atmospheric conditions that would one day make it not just possible, but absolutely necessary for life. Oxygen was no longer merely a toxic byproduct of photosynthesis. It was becoming a genuine force in the planetary system, and eventually it would tip the chemical scales completely, changing the composition of air and ocean and altering forever what life could become. If you had somehow found a way to stand on solid ground during the Archean, beneath that dimmer sun, above those greenish seas, breathing air that would kill you in moments, there would have been something else that felt distinctly strange without you quite being able to name it. The day would pass too quickly. A full rotation of the Earth took only about 14 hours, give or take. The reason for this has nothing to do with the atmosphere or the crust or anything happening on the surface. It's purely a matter of physics, baked into how the Earth formed and how it has been changing ever since. After the planet's violent beginning, and especially after the giant impact that created the Moon, the Earth was left spinning much more rapidly than it does today. That rotational momentum has persisted over billions of years, but it's been gradually slowing down through a process that continues right now. The mechanism behind that slowdown is the Moon itself, working through gravitational effects that are subtle but absolutely relentless. The interaction between Earth and Moon causes tidal friction, a constant but gentle drag, as ocean water tries to align itself with the Moon's gravitational pull, but lags slightly behind due to our planet's rotation. That friction gradually transfers angular momentum from the Earth to the Moon, pushing our satellite slightly farther away while simultaneously slowing Earth's spin. The result, over geological time, has been steadily longer days, but during the Archean, this process was still in its very early stages. The Moon was much closer to Earth than it is today, perhaps only about 200,000 kilometers away, less than two-thirds its current distance, and the tides it caused were correspondingly more extreme, more dramatic and more influential in shaping coastal environments. Ocean bulges were larger and more pronounced. Coastal zones experienced stronger, more dramatic shifts in water level throughout each day, and the Earth itself rotated quickly, completing a full spin in significantly less than two-thirds the time it takes today. This shorter day had consequences that extended far beyond simple timekeeping. Faster rotation meant stronger Coriolis effects, which directly influence wind patterns and ocean currents. It meant shorter exposure times to sunlight for any given location, which could significantly impact surface heating patterns and indirectly affect climate dynamics on both local and global scales. And for early life, especially photosynthetic microbes that depended on light for energy, it meant that the fundamental rhythm of light and dark cycles was completely different from what modern organisms experience. The microbial mats growing in shallow seas and tidal flats had to adapt to this rapid rhythm. Daylight hours came and went much more quickly than they do today. The window for active photosynthesis was narrower, more intense, and followed by longer periods of relative darkness. Night fell sooner, but it also ended sooner. That shift in timing affected everything from metabolic cycles to growth rates to the internal organization of microbial communities. Some organisms may have evolved to maximize energy capture during short but intense bursts of sunlight. Others might have developed sophisticated internal rhythms, primitive circadian mechanisms, to anticipate the rapid changes between light and dark and prepare their cellular machinery accordingly. It's not entirely clear how tightly early microbes were coupled to daily light cycles, but it's reasonable to think that the rhythm mattered significantly. Photosynthesis is inherently sensitive to light availability, and growth rates change depending on the balance between energy production during the day and energy storage and utilization during the night. A 14-hour day would definitely affect how organisms managed these processes, especially in environments where competition for resources was intense, and efficiency could mean the difference between survival and extinction. The shorter day also meant significantly more days per year. The Earth's orbital period, the time it takes to complete one trip around the Sun, hasn't changed appreciably since the Archean, but with shorter rotational periods, there were many more rotations within each orbital cycle. That translates to more sunrises and sunsets, more complete light-dark cycles, and more tidal cycles packed into each year. The frequency of tides in particular would have been quite striking. Some coastlines might have experienced multiple significant tides per day, each one stronger and more dramatic than anything we see in modern oceans due to the moon's proximity. That tidal energy had important geological effects, as well as biological ones. It helped stir shallow seas, driving sediment redistribution, and creating the kind of mixing that brings nutrients up from deeper water. In coastal zones where water levels rose and fell dramatically and regularly, microbial mats would have found both tremendous opportunities and significant challenges. Tides could expose mats to air and intense UV radiation briefly, triggering chemical changes and sometimes causing damage, but they could also erode and reshape existing habitats, forcing communities to rebuild and potentially opening up new surfaces for colonization. The constant disruption was also a source of renewal. Tidal action moved nutrients around, helped oxygenate shallow water layers, and created the kind of dynamic environment where evolution could experiment with new strategies and adaptations. The stronger tides and faster planetary rotation may also have contributed to more intense ocean mixing on a global scale. In an Archean world where surface water had a very different chemistry from deeper water, vertical mixing was extremely important for biological productivity. It helped cycle nutrients between different parts of the ocean system. It allowed oxygen produced by photosynthesis near the surface to penetrate slightly deeper into the water column, and it distributed iron, sulfur, and other chemical compounds in ways that directly affected microbial metabolism and evolution. A faster rotating Earth wasn't just spinning more quickly, it was actively churning itself, subtly but constantly, in ways that influenced everything from local weather to global ocean circulation. For the planet as a whole, faster rotation meant more intense and dynamic weather systems. Wind patterns were shaped differently by the enhanced Coriolis effect. Storms, if they existed in forms we would recognize, would have behaved in ways that seem quite unfamiliar by modern standards. Atmospheric circulation, though still primitive compared to the complex systems we see today, was definitely influenced by the rotational speed. That means the large-scale cells of rising and falling air that drive planetary climate, the conveyor belts of atmospheric heat transport, may have been narrower, faster, and more numerous. Even the physical shape of Earth itself was slightly different due to the rapid rotation. Faster spin created more centrifugal force, which caused the planet to bulge more prominently at the equator. That equatorial bulge would have affected ocean depth distribution, gravitational field strength, and even the way water moved across the surface. None of these differences were enormous on a human scale, but they accumulated over billions of years to influence how continents formed, how seas behaved, and how life adapted to its planetary environment. And all of this was happening silently, automatically, in a world without clocks or calendars or anyone to measure the passage of time. Time moved at its own pace set by fundamental physics and slowed gradually by the gravitational influence of the moon. Life simply adjusted to whatever rhythm the planet provided. It had no choice in the matter. The rotational dynamics of Earth weren't optional or negotiable. They were simply part of the background conditions that shaped what could evolve and how organisms would need to function in order to survive. The most striking aspect of this isn't that days were shorter during the Archean. It's the realization that they have been lengthening ever since, continuously and predictably. Every century, Earth's rotation slows by a tiny fraction of a second. The moon continues to drift away at a rate of a few centimeters per year, and the tides continue to act like a gentle but persistent brake on our planet's spin. It's barely noticeable over human lifespans, but over billions of years it fundamentally changes the structure of time itself. What we call a day is not a fixed, eternal unit. It's a moving target, slowly but constantly evolving as our planet ages. In the Archean, no one was watching the sky or measuring the hours, but time was definitely passing, and the way it passed, quickly, with more cycles per orbit, more tides per day, and more sunrises per year, left its permanent imprint in the geological record. Not in clocks or written records, but in sedimentary rocks, in ripple marks preserved on ancient shores, in the layered stromatolites that responded to light and dark cycles, in the wear patterns of rocks shaped by water that rose and fell in regular, tireless rhythm. The Earth was rotating rapidly, moving forward through space, dragging everything along with it. Microbes and minerals, oceans and atmosphere, all bound together by motion through both space and time. Time that was not yet counted in 24-hour days. Time that spun by faster than we can easily imagine, but still slowly enough to allow the gradual, patient construction of an entire world. The early Earth didn't have much going for it in terms of protection from the hostile environment of space. No ozone layer to filter deadly radiation, no thick atmosphere of breathable gases, no protective forests or vegetation of any kind. But beneath all the surface chaos, below the unstable crust, beyond the reach of volcanism and weather, something crucially important was working steadily in Earth's favor. Something silent, planetary in scale, and absolutely persistent, a magnetic field. This field didn't announce itself with any visible signs. You couldn't see it, hear it, or feel it directly. But it was definitely there, extending far out into space in invisible arcs and loops, deflecting charged particles from the sun and the wider galaxy. These particles, solar wind, cosmic rays, high-energy radiation of various kinds, bombard planets throughout the solar system with relentless intensity. They can strip away atmospheres molecule by molecule, shred complex organic compounds, and turn planetary surfaces into radiation-blasted wastelands, incapable of supporting any form of life. But Earth had a shield, an invisible protective barrier generated from deep within its own interior. The magnetic field originated in the core, in the very heart of the planet. Deep inside the Earth, the inner core was likely already beginning to solidify, or at least starting that slow process. Around that solid center, the outer core remained molten, a layer of liquid iron and nickel under enormous pressure, moving in vast, complex convective patterns, driven by heat flowing from the interior toward the surface. As this electrically conductive fluid moved through its convective cycles, it generated electrical currents. Those currents in turn produced magnetic fields. The process is known as the geodynamo, a self-sustaining system where motion creates electrical current. Current creates magnetic field, and the magnetic field influences the motion, creating a stable feedback loop. The result is a planetary magnetic bubble extending tens of thousands of kilometers into space, far beyond the atmosphere. This magnetosphere doesn't stop solar wind completely. That would be impossible given the enormous energies involved. But it diverts most charged particles around the planet, traps some in radiation belts, and prevents the constant erosion of Earth's atmosphere that would otherwise occur. Other planets in our solar system weren't quite so fortunate. Mars, for example, may once have had its own protective magnetic field, but that field faded relatively early in the planet's history. Without that protection, solar wind gradually stripped away most of the Martian atmosphere over hundreds of millions of years. What remained was thin, cold, and completely incapable of supporting liquid water on the surface. Earth, by contrast, managed to hold on to its atmospheric envelope, not just because it was the right distance from the Sun, but because it kept its internal dynamo active and running. In the Archean, this magnetic protection was absolutely critical for the development and persistence of life. The Sun was more active during its youth, more volatile, more prone to producing frequent solar flares and intense bursts of charged radiation that could have been devastating to any unprotected planet. Earth's atmosphere, still developing and relatively thin by modern standards, had very little capacity to block high-energy particles on its own. Without a magnetic field to deflect most of this radiation, much of the planet's water and air might have been lost to space over geological time, pulled upward and flung away by the constant assault of solar wind. The magnetic field also helped preserve the chemical stability of the upper atmosphere, reducing the loss of hydrogen that might otherwise have escaped into space and helping maintain the conditions necessary for liquid water to persist on the surface. It didn't make the Archean Earth a safe, comfortable place by any means, but it made the world survivable for the kinds of life that were just beginning to evolve and spread. Early life, still microscopic and confined mostly to ocean environments, may not have needed to understand any of the physics involved, but it benefited constantly from this invisible protection. UV radiation from the Sun was still a serious problem, since there was no ozone layer to absorb it before it reached the surface. But the most dangerous cosmic particles, the ones with enough energy to break chemical bonds and disrupt biological processes directly, were largely deflected or absorbed before they could reach the lower atmosphere or ocean surface. That reduction in radiation exposure allowed more stable environments to develop, especially in water where life could take additional shelter. Magnetic fields don't leave obvious traces in the fossil record the way biological structures do, but they do leave subtle clues in the rocks that geologists can read and interpret. Certain minerals, especially those containing iron, tend to align themselves with the prevailing magnetic field during the process of rock formation. When lava cools or sediments are deposited, these magnetic mineral grains lock into place, preserving both the direction and strength of the ancient field. Studying these alignments, a technique called paleomagnetism, allows scientists to track the history of Earth's magnetic field over geological time. From Archean rocks, we know that a magnetic field definitely existed during this early period. It was probably weaker than today's field, and possibly more chaotic or variable, but it was present and strong enough to deflect solar particles and help retain the atmosphere. This invisible system, born from the deep Earth processes that we're only beginning to understand, was essentially a quiet partner in the survival and evolution of early life. It also played subtle but important roles in atmospheric and space physics, influencing how auroras formed, where radiation was deposited in the upper atmosphere, and how the ionosphere behaved. These effects might seem minor, but they're actually quite widespread in their influence. They help shape atmospheric chemistry, affect the distribution of energy in the planet's upper layers, and create the kind of stable electromagnetic environment that complex chemistry requires. In a time before biology had developed sophisticated protective mechanisms, before there were shells, thick cell walls, or DNA repair systems, these planetary-scale protections were part of the basic operating conditions that life had to work with. Some hypotheses even suggest that hydrothermal vents, among the most likely cradles of early life, might have been influenced by local magnetic variations, either through the magnetic properties of the surrounding rocks or through electrical conductivity in the hot, mineral-rich water. It's still speculative, but it underscores the idea that magnetism wasn't just a planetary defense system operating at a distance. It may have shaped the actual environments where life first emerged in ways we don't yet fully understand. Over geological time, Earth's magnetic field has fluctuated significantly. It has reversed polarity many times, strengthened and weakened, and shifted its configuration in response to changes in the core. But it has never stopped functioning entirely, at least not for any extended period. As long as the core has remained active, and it shows no signs of shutting down anytime soon, the protective shield has remained in place, working silently and continuously. And as Earth's surface environment changed over billions of years as continents formed, oceans evolved and life became increasingly complex, the magnetic field stayed in place, always silent, always working, always providing the kind of background protection that allows surface processes to proceed without constant disruption from space. Today, we depend on this magnetic protection without thinking about it consciously. It guards our satellites and space stations. It guides the navigation of migratory animals. It helps define what we call space weather and protects our technological civilization from solar storms. But its roots extend all the way back to a time when Earth's interior was much hotter, its crust was thinner and more unstable, and its surface chemistry was still raw and experimental. In that ancient world, life had almost no defenses of its own against the hostile environment of space, except this one crucial shield, a planetary magnetic field generated from below, reaching out into the void and holding back the worst of what the universe had to offer. Even now, we don't fully understand how long this protective field has operated without major interruption, or exactly how the geodynamo process began in the first place, but its presence during the Archean is clear from the geological evidence. It was there when the air couldn't be breathed, when the sky was painted in alien colors, when the water was green with dissolved iron, and when microbes were just beginning to layer themselves into domes of sediment in their quest to reach the sun. The magnetic field shielded all of this activity without fanfare, without recognition, but quite effectively, and that invisible protection was enough to make the crucial difference. While oxygen chemistry was still being worked out, while continents were still deciding whether to form, and while days passed in those rapid spinning cycles, the magnetic field was already fully operational, protecting Earth's surface before anything on that surface even knew what danger looked like. And with that protection quietly in place, life had the opportunity it needed to keep going, to explore new possibilities, to evolve in response to challenges, and to wait patiently for the world to slowly change around it. It's almost impossible to imagine Earth without life, and not just because we can't picture the landscape visually. The real challenge is imagining the silence, not the kind of quiet you might find in a peaceful forest, or during a still morning, but something much deeper and more profound. A silence that had never heard wind moving through leaves, or grass rustling in a breeze, or the chirp of a single living creature anywhere on the planet's surface. During the Archean, the land areas were lifeless in every conceivable way. There were no plants of any kind, no insects, no animals, no organisms of any sort living on dry ground, no roots holding soil together, no leaves capturing sunlight. The very concept of a tree hadn't been invented yet by evolution. Even the idea of soil is somewhat misleading when applied to the Archean landscape. What little material covered the solid bedrock was not soil in any modern sense. It was simply loose rock, fragmented by physical weathering or volcanic activity, occasionally moved around by wind or water or tidal action, but never modified by biological processes. Without plants to break down rock with their roots, without fungi to decompose organic matter, without bacteria to fix nitrogen or cycle nutrients, the land surface was just exposed stone, volcanic flows, and whatever loose debris could accumulate before being washed away by the next rainstorm. There were no forests, obviously, but also no meadows, no grasslands, no shrubs or bushes. Without moss or lichens, organisms that would evolve much, much later, there were no pioneer species clinging to rocky surfaces and beginning the slow work of biological transformation that we see everywhere today. The continents, or the few substantial land masses that existed, were utterly barren. Their surfaces were often jagged and sharp, unstable and constantly changing. Volcanic flows created basaltic plains that stretched for kilometers. Slowly forming protocratons provided some of the first stable high ground. But all of it was naked rock, exposed to the elements without any biological protection or modification. Erosion certainly happened, but without plant roots to anchor loose material in place. It was often catastrophically rapid. Rain would fall and carve deep channels in loose volcanic ash. Wind would lift particles and carry them vast distances before depositing them elsewhere. But there was no ecosystem to moderate the violence of these physical processes, no vegetation to slow water flow, no organic matter to help bind particles together, no biological systems to capture and hold onto nutrients. And this brings us to that profound silence that characterized the Archean land surface. In a world without birds, mammals, amphibians, or even insects, the continents would have been overwhelmingly, almost impossibly quiet. No buzzing, no chirping, no howling or roaring, no chorus of night sounds or dawn songs. The only sounds would have been geological and meteorological. Wind, but even that would have sounded strange and different. Without trees or vegetation to interact with moving air, wind would have moved across bare rock and open ocean in ways that produced completely unfamiliar acoustics. It wouldn't whistle through leaves or rustle through grass. It would scrape across stone surfaces, echo through volcanic ridges and rush across barren slopes, carrying no trace of biological activity. The crash of ocean waves certainly existed, though even the coastlines were shaped very differently from what we see today. Tides, especially with the moon much closer than it is now, were dramatically more intense. Water struck rocky shores with tremendous force, and over time these impacts carved and shaped the edges of the land masses. But those waves carried no seaweed, tossed no shells onto beaches, and created no tide pools filled with diverse marine life. There were no sandy beaches populated by burrowing creatures, no coastal wetlands, no estuaries teeming with biological activity. Just water and rock grinding against each other in an endless cycle that had no biological witnesses or participants. Occasionally, volcanic activity would break the geological monotony. Explosions, deep rumbles, the hiss of gas releases. Ash clouds could darken the sky for days or weeks. Lava flows could pour dramatically into the ocean, sending up enormous plumes of steam and creating temporary islands. But even these dramatic events were followed by silence. No animals fleeing the eruption, no ecosystem disrupted and then slowly recovering. The land simply endured these episodes and returned to its baseline state of barren quiet. Even underground, there was no biological activity in the sense we understand it today. No earthworms aerating soil, no insects burrowing through organic layers, no roots penetrating deep into rock cracks and slowly breaking stone apart. The Earth's crust moved and shifted and cracked under tectonic forces, but it did so without any biological participation or influence. Life had not yet learned how to colonize terrestrial environments of any kind. The colors of this landscape reflected its biological emptiness. No green anywhere, obviously, mostly greys and blacks and browns, the natural colors of volcanic rock and weathered stone. Occasionally there might be chemical staining from mineral deposits, reddish iron oxides, yellow sulfur accumulations, pale crusts left behind by evaporated water. But nothing resembling the rich, varied palette of a world where life has gained a foothold on land. No seasonal changes, no spring blooms, no autumn colors. The land didn't change with the seasons because there was nothing living on it to respond to seasonal cycles. Sunlight hit the surface without any interference or filtering. No forest canopy to create dappled shadows. no grasslands to bend and wave in the breeze. On clear days, UV radiation reached all the way to the ground completely unimpeded. On days when volcanic haze or methane smog filled the atmosphere, the light would dim and take on strange colors, but even then nothing stirred in response to these changes. The Earth simply rotated under its alien sky, unobserved and unmodified by terrestrial life of any kind. And yet, life in the oceans was definitely aware that land existed. It might not have lived on the continents, but it certainly felt their presence and influence. Rivers carried nutrients down from these rocky slopes, delivering dissolved minerals to the shallow seas where microbes thrived. Erosion constantly added new chemical elements to the ocean system: iron, silica, sulfur, phosphorus, that became essential building blocks for biological processes. Volcanic activity poured heat and gases into the water, creating the kinds of hydrothermal systems that supported some of the planet's most active ecosystems. The land and ocean weren't separate, isolated systems. They were in constant communication through the water cycle, through chemical weathering, through the transport of materials from high elevations to sea level. Eventually, that silence would end. Microbes would begin to colonize moist surfaces near the water's edge. Over extremely long timescales, they would adapt to desiccation, to intense radiation, to nutrient-poor environments, and to the daily cycle of wetting and drying that characterizes the boundary between land and sea. They would eventually form biological crusts, thin layers of microbial communities that could trap dust, fix nitrogen from the atmosphere, and survive in harsh terrestrial conditions. But during the Archean, those evolutionary experiments were still far in the future. The land remained comprehensively quiet. And yet, for all its emptiness and silence, the terrestrial environment was absolutely essential to the planetary system. It was where continental crust was actively forming, thick, buoyant blocks of rock that could resist subduction and provide stable platforms for future biological colonization. It was where chemical weathering processes began to draw carbon dioxide out of the atmosphere, slowly but steadily helping to regulate the planet's climate. It was where the geological record of Earth's deep history was being written in layers of volcanic rock, sedimentary deposits, and minerals altered by water and heat. Even in its biological silence, the land was accumulating and storing information about environmental conditions, tectonic processes, and atmospheric chemistry that scientists can still read and interpret today. Today, it's extraordinarily difficult to find any landscape that remains completely untouched by biological activity. Even the harshest deserts hum with microbial life. Even the most barren cliffs and rocky outcrops host specialized communities of moss, lichens, or bacteria. But the Archean land was untouched in the most complete sense possible, not pristine like a protected wilderness area, but genuinely unclaimed by life, unused as habitat, unconverted by roots or reshaped by animals. It was raw planetary surface, neither home nor refuge for any form of life, but simply rock and weather and time. The silence of that ancient land wasn't peaceful or restful. It wasn't the quiet that comes after noise has stopped. It was the deeper silence of absence, not just the absence of sound, but the absence of biological participation in the world. Nothing breathed there, nothing lived there, nothing died there or struggled to survive. Nothing tried to take shelter or find food or reproduce. It was Earth, but not yet a home for anything beyond geology itself. And from the perspective of life thriving in the ocean, the land must have seemed distant, irrelevant, perhaps even hostile. But it was part of the same integrated system. The same water cycle that shaped coastlines also delivered nutrients to the sea. The same volcanoes that built islands also altered ocean chemistry. The same tides that exposed microbial mats also carved channels in the rocky shore. The land was part of the feedback loop that connected atmosphere, ocean, and solid earth, even if no living thing had yet figured out how to make use of it directly. One day, that situation would change dramatically. Life would begin to climb out of the ocean, to colonize moist surfaces, to survive exposure to air and sunlight, to breathe atmospheric gases and extract nutrients from rock. But for now, during the Archean, the land stood in comprehensive silence, unencumbered by biology, unbroken by roots, unmodified by the presence of life. And above it stretched a sky with no birds. Below it lay a world building slowly towards something far more complex. The Archean Earth was hot, but not in the way we usually think about heat. It wasn't dotted with flames or blazing with open fires, because fire in the conventional sense couldn't really exist yet. Fire, as we understand it, requires oxygen for combustion. It's a chemical reaction where fuel meets air and heat does the rest of the work. But the Archean atmosphere had essentially no oxygen available for burning. There were carbon-based materials everywhere, volcanic gases rich in combustible compounds, and plenty of heat from various sources. But without oxygen, the spark simply couldn't catch and spread. There could be no flames anywhere on the planet's surface. So instead of fire, the heat came from below, from the planet's interior, which was still radiating enormous amounts of energy left over from its violent formation. Heat from radioactive decay of unstable isotopes, heat from residual energy trapped in the core, heat from the constant motion of tectonic processes. That thermal energy moved steadily upward through the mantle, reaching the surface through volcanic eruptions and lava flows, through steaming fissures and molten plains that stretched across vast areas. Lava poured out constantly, not always in sudden, explosive bursts like some modern volcanoes, but often in broad, slow sheets of basaltic flow that covered entire landscapes and built new ground layer by layer. There were places on the Archean Earth where rock barely had time to solidify and cool before being buried again under another layer of molten material. The crust was much thinner during this period, more flexible and prone to cracking under pressure. Heat moved through it more directly and efficiently than it does today. Volcanic islands emerged from the sea and then vanished again under new eruptions. Ocean ridges split open continuously, oozing molten rock into the water. Even areas that weren't actively erupting were often hot just beneath the surface. Geothermal gradients were much steeper than they are now, meaning you didn't have to dig very deep to encounter temperatures hot enough to boil water or alter rock chemistry. The land, such as it was, often steamed without any visible flames, releasing water vapor and gases heated by contact with the hot rocks below. This constant geothermal activity made the Earth feel mechanically alive in ways that had nothing to do with biology. Not organic life, but dynamic, energetic, constantly changing. Heat altered water chemistry wherever the two came into contact. It built extensive hydrothermal systems that provided energy for some of the earliest forms of microbial metabolism. It fractured rocks and released minerals into the ocean, feeding nutrients to the growing communities of marine microbes. It created pockets of warm, chemically rich water where life could find shelter from UV radiation while having access to both energy and raw materials. Life during this period didn't just survive intense heat. In many cases, it actually required heat to thrive, but heat wasn't distributed evenly across the planet, and its absence didn't necessarily mean calm or stability. Just as fire couldn't exist without oxygen, ice couldn't form easily either, at least not in the dramatic glacial ways we see in later periods of Earth's history. There's ongoing scientific debate about just how cold the Archean Earth got during its cooler periods. Some climate models suggest the planet remained relatively warm throughout this eon, thanks to greenhouse gases like methane and carbon dioxide that efficiently trapped heat from the dim young sun. Other models propose that temporary cooling events did occur, that clouds of volcanic ash or shifts in atmospheric chemistry may have led to brief cold snaps, possibly even limited glaciation in some regions. But even if ice formed during these cooler intervals, it did so without the usual visual and geological signatures we associate with ice ages. There were no snowy mountain peaks, no polar ice caps stretching across continental areas, no massive ice sheets grinding slowly across the landscape and carving valleys into the bedrock. The land was too geologically active, the atmosphere too chemically different, And the ocean chemistry too, unlike anything we see today. If ice came to the Archean world, it came quietly and left relatively few traces. It didn't need to pile up in massive sheets to be dangerous to life, though even modest cooling could have serious consequences for the simple ecosystems that were just getting established. A significant drop in temperature could alter ocean circulation patterns, affect the solubility of important gases, and change the chemistry of shallow basins where microbial life was most active and productive. Cold snaps could slow photosynthesis rates, make nutrient cycling less efficient, and stress biological communities that had adapted to warmer conditions. Even small shifts in average temperature could have major consequences, not because life was particularly fragile, but because it was still relatively simple. With few backup systems and no complex interconnected ecosystems to provide stability, a failed microbial community might mean that nothing would successfully recolonize that particular area for centuries or longer. Still, the dominant climate throughout most of the Archean leaned toward the warm side of the spectrum. The sun, despite being in its early stages and giving off significantly less light than it does today, roughly 70 to 75% of current output, should theoretically have left the Earth completely frozen. By all rights, with that level of solar input, our planet should have been a snowball. But it wasn't, thanks to the greenhouse gases that made up for the solar shortfall. Methane was particularly abundant, produced both by early microbes and by various geological processes. Methane is remarkably efficient at trapping heat, much more so than carbon dioxide, and in the absence of oxygen to break it down, methane could build up to concentrations that would be toxic in today's atmosphere. This potent greenhouse effect kept the oceans liquid, maintained active weather systems, and kept surface temperatures within the range needed for liquid water to flow rather than freeze solid. But this wasn't a carefully calibrated, finely tuned system running in perfect balance. Too much volcanic activity, changes in weathering rates, or even shifts in biological activity could easily tip the thermal scales one way or the other. Cooling events may have occurred when volcanic ash blocked sunlight or when biological processes temporarily reduced methane production. Warming spikes probably happened when massive volcanic eruptions released extra carbon dioxide or when changes in ocean circulation affected heat distribution. The planet's temperature wasn't locked into a stable state. It drifted and fluctuated on geological timescales, sometimes gradually, sometimes more abruptly. Local conditions varied wildly depending on geological activity and geography. Shallow seas warmed by direct sunlight and geothermal heating could approach boiling temperatures in some locations. Deeper waters, cut off from surface circulation and sunlight, might remain cold, dense, and stagnant for long periods. Hydrothermal vent systems created isolated environments with extraordinary temperature ranges, from near freezing just a few meters away from the vent mouth to hundreds of degrees at the point where superheated water emerged from cracks in the seafloor. And on the land surface, bare rock would heat up dramatically under the hazy sun during the day, then radiate that thermal energy away rapidly at night. Without vegetation, soil, or any other insulating materials to moderate these temperature swings, the day-night cycle could produce surprisingly extreme conditions. There were no forests to hold moisture and create stable microclimates, no clouds formed by transpiration from plants, no living ground cover to soften the thermal extremes between day and night or between seasons. Rain, when it fell, hit bare stone or loose volcanic ash directly. It pooled in uneven basins and temporary lakes. It carved channels and gullies and ran off quickly toward the sea, largely unimpeded by biological processes. Water evaporated rapidly in some areas due to geothermal heating, but could also freeze in thin crusts when nighttime cooling was severe enough. And the atmosphere, with its strange mix of methane, carbon dioxide, and other gases, carried heat unevenly across the planet. Some regions would have been scorching hot, while others cooled too rapidly for comfort. There was no global thermostat, no planetary comfort zone maintained by the complex feedback systems that help regulate modern climate. And yet, life endured and even thrived within these challenging conditions. Because these thermal extremes, this heat without fire, this potential for cold without the familiar ice ages, weren't random chaos. They were simply the environmental conditions that life was born into and adapted to. Microbes didn't expect comfort or stability. They didn't wait around for ideal conditions to appear. They used whatever was available in their immediate environment. They built communities around hydrothermal systems that provided both heat and chemical energy. They adapted to UV exposure that would be lethal to modern organisms. They evolved metabolic pathways suited to high temperatures and chemical gradients that only existed within very narrow ranges of conditions. To us, the Archean world might look completely uninhabitable. No familiar colors, no breathable air, no oxygen, no comforting warmth from controllable fires. But to the life that evolved within that system, it was simply the world as it existed. Heat came from the planet's interior rather than from combustion. Cold came from a dim sun, and an atmosphere still learning how to trap and distribute solar energy, rather than from familiar ice and snow. The extremes weren't extreme to the organisms that lived through them. They were normal, predictable, part of the basic operating conditions of their world. And within those conditions, Earth's long experiment in biological complexity continued its course. With every lava flow, every volcanic winter, every fluctuation in methane concentrations or solar output, life adjusted its strategies. Not dramatically, not overnight, but steadily and persistently over geological time. Because while the Archean Earth didn't yet have fire or familiar ice ages, it definitely had energy. It had liquid water, and it had the potential not just for change but for the kind of persistence that could outlast any individual environmental crisis. In that sense, the Archean climate wasn't hostile to life. It was formative. It shaped what life could become by defining the limits within which evolution had to operate. And as the crust slowly cooled, as the days gradually lengthened, and as the chemistry of air and ocean began to drift towards something more familiar to us, that early life was ready to follow along. Molded not by comfort and stability, but by extremes that taught it to be resilient, flexible, and persistent above all else. The moon didn't hang peacefully in the Archean sky the way it does for us today. It wasn't a distant, gentle companion casting romantic light across calm oceans. It was much nearer, dramatically nearer, nearly twice as large in the sky, and more than twice as powerful in its gravitational influence on the Earth below. It was still moving away bit by bit, following the same physical laws that govern its motion today. But during the Archean, it was close enough to stir the seas like a massive spoon, and that proximity mattered enormously for life on the early Earth. The moon had already been around for a while by the time the Archean began. Its origin story was violent and spectacular, a planetary collision between the early Earth and a Mars-sized body that astronomers have named Theia. This impact was so massive that it tore apart much of Earth's early crust and threw enormous amounts of molten debris into orbit around our planet. That debris gradually coalesced and cooled to form the Moon, and the Earth-Moon system slowly settled into the gravitational relationship that continues today. But this was a relationship that began with chaos and tremendous energy. That energy had to dissipate somehow. Orbits had to stabilize, and the physical effects of this process lingered for hundreds of millions of years. In those early days, the moon wasn't just a visual feature in the sky. It was an active geological force. Its gravity pulled at the Earth with tremendous strength, deforming not just the oceans but the solid crust itself. Tidal bulges moved across the planet's surface as it rotated, creating friction that had measurable consequences. That friction converted kinetic energy into heat, slowed Earth's rotation, and gradually pushed the moon outward to a more distant orbit. The same physical dance continues today, but back then everything moved faster and hit harder and had more dramatic effects. Because the moon was so much closer, its tidal influence was correspondingly stronger. Current estimates suggest that Archean ocean tides may have been 10 times greater than anything we experience today. That means coastlines didn't just rise and fall gently. They changed dramatically. multiple times each day. Water would surge far inland, then retreat quickly, exposing vast areas of seafloor and then drowning them again in a regular, relentless rhythm. These tidal shifts weren't subtle or easy to ignore. They were major sculpting tools that carved shorelines, redistributed sediments, and created zones of intense chemical mixing that allowed nutrients to concentrate in areas shallow enough for photosynthetic microbes to use them effectively. For early life, this tidal energy was more important than sunlight alone in many environments. The tides created predictability and structure in a world that otherwise offered very little of either. They regulated access to light and nutrients in regular cycles. They exposed biological surfaces to the air, such as it was, and then submerged them again in mineral-rich seawater. This rhythmic disturbance became a kind of planetary metronome, a schedule that life could adapt to and eventually depend on. Microbial mats grew in patterns that directly matched tidal cycles. Colonies of organisms adapted to survive brief periods of exposure to air and intense UV radiation. Chemical reactions accelerated during the transitions between wet and dry conditions, when gradients were steepest and energy was most readily available. Without the moon's strong gravitational influence, that regular rhythm simply wouldn't have existed. The sun also creates tides, but solar tides are much weaker than lunar ones, and they don't produce the same high-frequency, high-amplitude changes that drove so much of Archean coastal ecology. The moon's gravity made the early Earth a dynamic, constantly changing world in ways that static chemistry alone could never have achieved. It stirred the water, it pulled at the land, it drove circulation in shallow basins, and it may have influenced ocean mixing on a truly global scale. And it directly shaped the length of each day. As Earth's rotation gradually slowed due to tidal friction, the length of a day increased from a frantic few hours immediately after the moon's formation to about 14 hours during the Archean to the 24-hour cycle we experience now. This change was slow but absolutely relentless, and it altered everything from wind patterns to energy distribution to the fundamental rhythm of life itself. The moon's position in the sky wasn't constant, of course. It still rose and set, moved through its phases from new to full and back again. But because it was so much closer than it is today, it would have appeared enormous in the sky, filling a substantial portion of the horizon when it was visible. It glowed not with its own light, but with the reflected radiance of that young, dim sun. There were no eyes to see it, and no organisms living on land to watch it rise and set, but it was there every day and night, tugging invisibly at water and stone and time itself. We don't know exactly how geologically active the moon's surface was during the Archean. It was probably already cooling and stabilizing by then, but its impact on Earth was unmistakable and profound. The tides helped stabilize our planet's axial tilt, which is a major factor in long-term climate stability. Without the moon's gravitational influence, Earth's rotational axis could wobble dramatically over millions of years, swinging from nearly vertical to highly tilted in chaotic, unpredictable ways. With the moon present, our axial tilt stays within a relatively narrow range, keeping seasonal patterns predictable and helping maintain the temperature gradients that drive ocean circulation and atmospheric weather systems. And while the moon doesn't produce any light of its own, its phases would have created a secondary rhythm in the Archean world, a slower pulse of bright and dim nights, full moons and new moons reflecting across the alien oceans. For microbial life floating near the sea surface, this periodic change in nighttime illumination might have been detectable and biologically significant. For organisms living in tidal zones, the alignment of lunar and solar tides created especially extreme conditions, spring tides that reached much farther inland than usual, or neap tides that retreated more dramatically than normal. Eventually, the moon would become a reference point for human cultures, a timekeeper, a symbol, a source of inspiration for calendars and stories and scientific investigation. But in the Archean, it had no cultural meaning whatsoever. It was just gravity in motion, just physics in action, and yet its influence was absolutely profound and foundational. It helped regulate Earth's rotation and stabilize the climate. It drove ocean dynamics that were essential for early life. It gave the biological world something approaching a reliable rhythm and schedule in an otherwise unpredictable environment. Today, we rarely think consciously about the moon's ongoing influence on our planet. Tides seem passive and predictable. The moon feels distant and largely irrelevant to daily life. But it's still moving away from us, about 3.8 centimeters per year, and Earth is still slowing down as a result. In the far future, days will be even longer than they are now, and the moon will orbit even farther away. Yet its ancient role in shaping the early Earth remains permanently etched in the geological record, in banded sediments shaped by tidal currents, in the layered structures of stromatolites that grew in response to regular changes in water level, in the chemical signatures that record wet and dry cycles across billions of years, in the very existence of stable, long-lived continents that formed partly because tidal mixing helped concentrate the materials needed for continental crust. Back in the Archean, the moon wasn't just something that appeared in the sky at night. It was in the water, actively shaping ocean chemistry. It was in the rocks, influencing how sediments were deposited and preserved. It was in the very spin of the planet, affecting everything from weather patterns to the daily rhythm that life had to adapt to. The moon didn't speak or communicate in any way we could understand, but it moved, and the Earth, from its deep crust to its surface tides to the earliest living cells drifting in shallow, stirred seas, responded to that motion constantly and completely. There it was, leaking out slowly in small amounts, long before it could do anything that anyone would notice. Oxygen made by microbes quietly harvesting sunlight, splitting water molecules, and discarding what seemed like a waste product that nothing else needed or wanted. In the early oceans, cyanobacteria had already figured out the basics of oxygenic photosynthesis, a way to use water and carbon dioxide to build sugars and release chemical energy, and as a byproduct of this process, they released oxygen into their immediate environment. But the world had no place for that oxygen yet, no use for it, no way to accommodate it, no biological systems designed to take advantage of its unique chemical properties. The story of oxygen on Earth isn't one of immediate transformation or dramatic revolution. It's a story of waiting, of extremely slow accumulation, of persistent resistance from the environment, of everything in the ocean and atmosphere trying its best to neutralize, absorb, and bury oxygen before it could build up to significant levels. And for an extraordinarily long time, hundreds of millions of years, the environment succeeded in suppressing oxygen almost completely. In the Archean oceans, oxygen was consumed almost as quickly as it was produced. It reacted instantly and completely with iron dissolved in the seawater. Iron was abundant everywhere in the anoxic ocean, present in its reduced form, which remained perfectly soluble in water without oxygen around. When the first traces of oxygen encountered this dissolved iron, the reaction was fast and irreversible. The iron oxidized, became insoluble, and sank to the seafloor as precipitated minerals. This chemical reaction built the distinctive layered rock structures we now call banded iron formations, alternating bands of deep red and grey minerals that mark ancient episodes of oxygen production and immediate removal. These formations appear throughout the Archean timeline, serving as quiet but unmistakable evidence of a planet that was absorbing as much oxygen as it possibly could, as quickly as it could, every time any was produced. The oxygen generated by photosynthetic microbes also reacted readily with sulfides, methane, and other reduced compounds that were common in both the ocean and the atmosphere. These reactions stripped oxygen out of circulation before it could accumulate anywhere. They prevented it from building up in the water column, kept it from escaping into the air, and maintained the overall anoxic character of the planetary system. The oceans became the first battleground in a slow chemical war between production and consumption of oxygen, and life itself was inadvertently generating both sides of this conflict. Cyanobacteria and other photosynthetic organisms created oxygen through their metabolism, but other microbes consumed oxygen or produced compounds that neutralized it. Anaerobic life forms, those that had evolved to thrive without oxygen, actually found it toxic and worked to eliminate it from their environment. The balance between production and removal was always shifting, always delicate, never settling into a stable equilibrium. It wasn't just a matter of simple quantity either. It was about reaching critical thresholds where the chemistry of the system could change fundamentally. Oxygen had to reach a certain minimum level before it could begin to persist in the environment rather than being immediately consumed. Before the chemical sinks became saturated enough to allow any surplus oxygen to linger. Until that threshold was reached, every oxygen molecule produced was essentially erased from the system, leaving no trace except in the chemical signatures preserved in rock formations. And yet, the microbes kept producing oxygen anyway, not for any purpose we would recognize, not for the future benefit of other organisms, not as part of some plan or goal. They produced oxygen simply because it was a necessary byproduct of the photosynthetic process that allowed them to capture solar energy and convert it into biological growth. For the microbes performing photosynthesis, oxygen was waste, something they had to release in order to keep their energy-generating systems functioning properly. And that biological activity was driven by the most abundant energy source available, light from the sun. It came from above, filtered through haze and clouds and the strange atmospheric chemistry of the early Earth. But in the right locations, shallow seas, protected lagoons, tidal flats, it was sufficient to power extensive microbial communities. Microbial mats spread across underwater surfaces in dense layered carpets. They photosynthesized during the day when light was available. They processed nutrients and organic compounds at night. They built those distinctive dome-shaped stromatolites that we can still find in ancient rocks, and through all of this activity, they kept steadily leaking oxygen into a world that was completely unprepared to handle it. Some of that oxygen did manage to stick around in microenvironments, tiny zones within the mats themselves where local chemistry had shifted enough to allow oxygen to persist briefly. Thin surface layers of water where sunlight penetrated and oxygen concentrations could build up temporarily. These were like isolated islands of oxidizing chemistry surrounded by a vast sea of anoxic conditions. And in those small islands of chemical change, biology began to adapt and evolve. Some organisms developed biochemical systems to detoxify oxygen and protect themselves from its harmful effects. Others began to experiment with ways to exploit oxygen, to use its high reactivity as an energy source rather than simply enduring it as an environmental hazard. But these were still evolutionary outliers, living in chemical bubbles surrounded by a vast world that remained fundamentally hostile to oxygen and everything associated with it. Meanwhile, the slow, quiet assault of oxygen on the planetary system continued. It changed mineral formation processes, altering the way rocks formed and weathered. It affected weathering rates on land surfaces, though very gradually. It influenced the solubility of metals and other elements in seawater, creating chemical gradients that hadn't existed before. Each small change fed back into the larger system in complex ways. Some changes encouraged more oxygen production by creating better conditions for photosynthetic microbes. Others limited oxygen production by altering nutrient availability or water chemistry. The whole planet was involved, not just passively, but as an active chemical participant, in resisting and eventually enabling the rise of this highly reactive molecule. The extended wait for oxygen accumulation is sometimes called the oxygen lag, the enormous time gap between the evolution of oxygenic photosynthesis and the moment when oxygen finally began to accumulate in the atmosphere in significant quantities. That lag lasted for more than 1 billion years. For perspective, that's longer than all of multicellular life has existed on Earth. It's longer than the entire time since the first animals appeared in the fossil record. It represents an almost incomprehensible stretch of geological patience, during which the basic chemistry of the planet was slowly, incrementally being transformed. And during that entire period, Life was still experimenting and evolving and spreading into new environments. The absence of atmospheric oxygen didn't stop biological evolution. It just shaped the direction that evolution took. Anaerobic metabolisms remained completely dominant. Chemosynthetic communities around hydrothermal vents flourished and diversified. Microbes learned to use sulfur, nitrogen, hydrogen, anything except oxygen to power their survival and growth. In some cases, the gradual appearance of oxygen actually created biological stress. It killed off organisms that couldn't adapt to the changing chemistry. It forced life forms into new ecological niches, away from the zones where oxygen was beginning to accumulate. There may have been brief episodes, regional events, short-lived increases, when oxygen levels rose temporarily above the usual baseline, enough to affect local chemistry, but not enough to change the planetary system permanently. These were false starts, evolutionary experiments, chemical spikes that left traces in the rock record, but didn't lead to lasting transformation. The global system pushed back against these changes. The chemical sinks were still too strong, the balance still tilted heavily against oxygen accumulation. But something fundamental was shifting beneath the surface, slowly and inexorably. The chemical sinks that had been absorbing oxygen for so long were gradually filling up. Iron concentrations in the ocean were dropping as more and more iron was pulled out of solution and deposited as banded iron formations. Methane levels, once stabilized by a haze-producing atmosphere, began to fluctuate more dramatically. Oxygen's influence was gradually creeping outward from those isolated microenvironments, becoming harder to contain within small pockets of unusual chemistry. The stage was being set for a permanent, irreversible change. That change wouldn't happen until well after the Archean ended, during the Paleoproterozoic era, in what geologists now call the Great Oxidation Event. But all the groundwork was being laid during the Archean. The microbes were already there. The microbial mats were already widespread. The endless cycle of photosynthesis was already underway. The quiet, tireless leak of oxygen into a world not designed to handle it was already well established. And over deep geological time, that leak gradually became a trickle. The trickle would eventually become a steady flow, and ultimately the planetary chemistry would reach a breaking point where the old balance could no longer be maintained. What followed that breaking point would not be an immediate explosion of change, but rather a long, drawn-out transformation that would reshape the atmosphere, reorganize the biosphere, and create entirely new possibilities for biological complexity. Oxygen would rise gradually at first, then in sudden bursts, then settle into new chemical equilibria that had never existed before. The atmosphere would change its fundamental character. Entire groups of microbes would disappear, unable to survive in the new oxidizing world, while others would take their place and thrive. Complexity would become possible for the first time. Multicellular life would become feasible. The stage would be set for everything that followed in the history of life on Earth. But during the Archean, all of that remained in the future. The wait was still ongoing, and the world, strange and alien and largely breathless, continued its business. Volcanoes erupted, and islands rose from the sea. Continents slowly assembled from scattered fragments. Tides rose and fell under the pull of a closer moon. And life carried on, mostly unaware that it was quietly and persistently reshaping the composition of the atmosphere, one molecule at a time. The long wait for oxygen wasn't a pause in Earth's development, it was an active process, moving quietly but relentlessly through sunlight and sediment, through the layered films of microbial communities, through the chemistry of seawater and the mineral formation processes in the planet's crust. And when the balance finally did tip, when the threshold was finally crossed, the world would never be quite the same again. It's a fair question, and an important one. If you're standing on a beach today or hiking a mountain trail, you're surrounded by things you can see and touch directly: trees, rocks, animals, clouds, flowing water. But the Archean Eon is so impossibly far back in time. It's not just before human civilization or before recorded history. It's before bones, before shells, before leaves, before any of the things that usually fossilize and end up in museum displays or geology textbooks. So how can we possibly know what Earth was like during that ancient time? How can we determine what the atmosphere contained, what the oceans were made of, what the landscape looked like, and what kinds of microbes were doing in the shallow seas? We know because the Earth remembers, even if it doesn't remember clearly or completely. Our planet keeps detailed records in stone, not photographs or written accounts, obviously just physical and chemical patterns left behind by ancient processes. And if you know how to read those patterns carefully, you can reconstruct significant aspects of the world as it once was, not with perfect certainty or complete detail, but with enough reliable clues to form a scientifically coherent picture. The oldest physical pieces of our planet that we still have access to are rocks, and some of them are more than 4 billion years old. The most durable are zircon crystals, a particularly resilient mineral that forms in molten environments and can survive even when all the surrounding rock has been destroyed, altered, or recycled. Zircons contain trace amounts of uranium, which decays radioactively into lead at a precisely known rate. By measuring how much lead has accumulated inside individual zircon grains, scientists can determine their age with remarkable precision, sometimes down to a window of just a few million years, which is quite impressive when you're dealing with events that happened more than 3 billion years ago. Some zircons are found embedded inside much younger rocks, which tells us not just how old the mineral grains are, but also something about the environment they originally formed in. Their chemical composition contains subtle hints about the water they crystallized from. Oxygen isotope ratios, for example, strongly suggest that liquid water existed on Earth's surface as early as 4.3 billion years ago, even before the Archean Eon officially began. Other types of rocks, especially banded iron formations, provide direct records of oxygen activity in ancient oceans. These are distinctive sedimentary structures made of alternating layers of iron-rich minerals and silica-rich layers. They only form under very specific chemical conditions. Lots of dissolved iron in the ocean water, combined with periodic exposure to small amounts of oxygen. The oxygen would cause iron to oxidize and precipitate out of solution, settling onto the seafloor in distinct layers. Then, when oxygen concentrations dropped again, silica-rich material could settle out separately. Layer after layer, this pattern repeated over thousands of years, and when we find banded iron formations in rocks of Archean age, we're looking at a direct record of oxygen production and removal written into the structure of the seafloor itself. There are also subtle but detectable isotopic fingerprints left behind in ancient carbon deposits. Life tends to preferentially use the lighter isotope of carbon, carbon-12, over the heavier carbon-13 isotope. When ancient microbes photosynthesized or metabolized carbon-based molecules, they left behind organic material that was enriched in the lighter isotope. These biological signatures, preserved in sedimentary layers, suggest active biological processes even in the complete absence of body fossils or other direct evidence. When we analyze carbon isotope ratios in rocks dated to more than 3.5 billion years ago, we find clear hints of life, not life we can see directly, but life that left a distinctive chemical shadow in the geological record. Sulfur isotopes tell an equally important part of the story. During the Archean, when the atmosphere contained little to no oxygen, sulfur cycled through air and water in ways that were completely different from modern processes. Volcanic gases released sulfur compounds into the atmosphere, and without oxygen present, these compounds underwent unusual photochemical reactions driven by ultraviolet light from the sun. These reactions left behind very specific isotope ratios, called mass-independent fractionation, that only occur in an oxygen-free atmosphere. We find these distinctive sulfur signatures in Archean rocks, and when they disappear from the geological record, it marks a major transition, the rise of atmospheric oxygen and a fundamental shift in planetary chemistry, visible only at the molecular level. In places like the Pilbara Craton in Western Australia, or the Barberton Greenstone Belt in South Africa, we can study remarkably well-preserved ancient sediments. These rock formations have been folded, buried, and metamorphosed over billions of years, but they still contain the basic structures and chemical signatures of Earth's early surface environments. In some of these ancient rocks, we even find stromatolites, fossilized microbial mats that built themselves up in layers over long periods of time. These aren't fossils of individual microbes, which would be too small and fragile to preserve, but they are fossils of what the microbes built, dome-like and columnar structures with fine internal layering that shows life was actively shaping its environment over geological timescales. Even the absence of certain features can tell us important things about ancient conditions. There are no animal fossils in Archean rocks, no plant impressions, no signs of oxygen-dependent minerals forming at the surface. That absence isn't just a gap in the record, it's a positive data point that tells us what the Earth could not yet support. We also study detrital minerals, grains of stable minerals like uraninite or pyrite, that would oxidize and disappear quickly in today's oxygen-rich environment, but could survive transport through rivers and streams in the Archean because the atmosphere was chemically reducing rather than oxidizing. Their presence in ancient sedimentary rocks is strong evidence that the air contained essentially no free oxygen when they were deposited. None of this geological detective work is simple or straightforward. These rocks are incredibly old, often altered by heat and pressure, fractured and folded beyond easy recognition. The isotopic signatures can be subtle and require sophisticated analytical equipment to detect reliably. The structures can be ambiguous, open to different interpretations. It takes careful comparison, extensive cross-checking, and often vigorous disagreement among scientists to build a coherent picture from fragmentary evidence. And yet, over decades of systematic research, that picture has gradually come into focus. We don't see the Archean world directly, of course. We see it refracted and filtered through the evidence it left behind, in mineral grains that still remember their formation conditions, in chemical ratios that preserve ancient biological processes, in structures shaped not by organisms themselves but by their behavior and metabolism, in sedimentary layers that still bear the influence of tides pulled by a much closer moon. And that's how we know, not from stories or eyewitness accounts, but from the physical consequences of what actually happened. The Earth, even in its most hostile and unrecognizable state, still followed the fundamental laws of physics and chemistry, and it left behind a record of those processes, encoded in stone. As long as you know how to look for it and interpret it carefully, there's a tremendous amount of information preserved in the rocks. It's not a perfect record, certainly. There are major gaps where entire continents have been subducted back into the mantle. Cratons have been broken apart. Ancient rocks have been erased by erosion or destroyed by later geological processes. The Archean archive is fragmentary and often difficult to interpret, requiring careful analysis and always leaving room for uncertainty and debate. But it's sufficient to tell a coherent story about our planet's deep, not in perfect detail or full color, but clearly enough that we can say with confidence, this is what it was probably like. This is what life was doing. This is how the world began, the long, slow process of becoming itself. And in that story, we find ourselves, not directly, not immediately, but distantly connected across billions of years. Because everything we are, everything we depend on, everything that makes our modern world possible, ultimately traces back to that quiet, ancient, alien time. The world with no breathable air, no trees, no fire, no familiar sounds, just rock and water, and light and time, and the first stubborn, persistent signs of life writing its story molecule by molecule into the only surface available to it. By the time the Archean Eon gave way to the Proterozoic that followed, the Earth hadn't changed all at once. There was no sudden shift in color, no dramatic line drawn across the geological timeline. The rocks didn't notice any particular boundary. The microbes didn't pause to acknowledge a transition. The planet simply kept rotating, just a little bit slower than before. The sun kept rising over oceans that still held no fish, and the air, still mostly unbreathable by our standards, had just the faintest trace of something new and unprecedented in it. This is how change really works on a planetary scale. Quietly, gradually, with long periods of apparent stability, punctuated by brief episodes of more rapid transformation. But even the rapid changes are slow by human standards, and the truly dramatic shifts rarely reverse themselves completely. The Archean didn't end because it was finished or complete. It ended because the fundamental conditions that had defined it, the atmospheric chemistry, the internal heat budget, the stability of the crust, the pace of geological processes, had slowly shifted until they represented something genuinely different. Oxygen had finally begun to accumulate in places where it couldn't persist before. The photosynthetic microbes were still working much as they always had, but the chemical sinks that had been absorbing their oxygen waste were finally weakening and filling up. Iron was becoming harder to find in dissolved form. Sulfur chemistry was changing in measurable ways. The ocean and atmosphere were no longer able to completely suppress oxygen accumulation, and that one change would eventually unlock everything else that followed. The continents, once just scattered fragments of unstable crust, had started to come together into larger, more coherent assemblies. Not full supercontinents yet, but substantial land masses that could persist for hundreds of millions of years. They moved slowly and collided occasionally, building mountain ranges that would be eroded down and replaced by new ones. The cycle of rock formation, weathering and recycling had deepened and become more complex. Life itself was still microscopic and mostly invisible, but it was beginning to alter its surroundings in ways that left increasingly clear traces in the geological record, not just subtle chemical signatures in isotope ratios, but layers of organic material building up faster than before. Biological processes were becoming more efficient, more widespread, and more influential in shaping the chemical environment of both ocean and atmosphere. Life was no longer simply adapting to whatever Earth provided. It was actively participating in the construction of the world it lived in. Even the sky was different by the end of the Archean. The methane haze that had once dominated the atmosphere was beginning to thin as oxygen slowly rose and methane became less stable. Blue wavelengths of light were starting to penetrate more successfully through the changing air, not consistently, not everywhere, but often enough to hint at the blue skies that would eventually become normal. The sun was still dimmer than today's, but it was steady and predictable. The moon had drifted slightly farther away, making the tides somewhat calmer and the days marginally longer, though still much shorter than we're used to. The same fundamental physical forces were still operating: gravity, electromagnetism, nuclear processes, but they were working on a planet that had become subtly but significantly different from the one they had shaped during the early Archean. And through all of this gradual transformation, the Earth had never stopped remembering. It continued to layer new stories into the rock record, preserving heat in the core, tracing patterns of magnetic field changes, recording the slow evolution of life in chemical signatures that we can still detect and analyze today. The planet didn't know it was writing history, but it was, constantly and automatically, in every mineral grain that crystallized, every sediment layer that accumulated, every isotope ratio that reflected biological processes. When we talk about the Archean today, we're not really talking about something that's completely gone and finished. We're discussing the part of Earth that still exists in the deepest, oldest rocks of the continental cratons, in the fundamental mineral composition that forms the foundation of our modern continents, in the legacy of microbial metabolisms that continue to operate in similar ways today, in the oxygen we breathe, which is the direct descendant of those first hesitant experiments in photosynthesis. We carry Archean history in our cells, in the biochemical pathways that extract energy from food, in the DNA repair mechanisms that protect us from radiation damage, in the basic cellular structures that all life still uses. We carry it in our sky, where the magnetic field, generated by the same geodynamo processes, still deflects cosmic radiation. We carry it in the 24-hour rhythm of our days, still slowing gradually as the moon continues its ancient drift away from Earth. The Archean didn't really end. It simply transformed into the Proterozoic Eon, a new chapter with a different atmosphere, a different pace of change, and eventually radically different forms of life. But even then, the foundation remained essentially the same. The continents were still built on Archean cores. The first principles of biology were still operating according to rules established during that ancient time. Earth was no longer truly young, but it wasn't yet mature either. It was learning how to host not just life, but increasingly complex life, not just chemistry, but organized, structured, multicellular biology. And perhaps that's the best way to summarize what the Archean really was. The time when Earth figured itself out. Not consciously, not according to any plan, but through the slow, patient operation of physical and chemical processes that built steadily towards something more complex and more interesting. Fire would come later when there was finally enough oxygen to support combustion. Breathing would evolve when the atmosphere could sustain it. Trees and forests and animals with eyes would all appear in their proper time. But none of that could happen until this foundational work was complete, until the planet had built stable continents, established reliable water cycles, developed protective magnetic fields, and allowed life to gain its first tentative foothold in the shallow seas. And now that work was finished, not perfectly, not completely, but sufficiently, the Archean was giving way to something new, and the long story of Earth's development was entering its next major phase. So if you've listened this far, whether you're lying in bed under familiar stars, walking through landscapes shaped by billions of years of geological history, or drifting towards sleep in a world that couldn't exist without that ancient foundation, thank you for taking this journey with us. Thank you for slowing down and being curious, for letting this story unfold at the pace the Earth itself set, slowly, steadily, and without any need for a dramatic ending. The Archean didn't conclude with fanfare or celebration. It just kept going, transforming gradually into something that would eventually lead to forests and mountains and cities, and the kinds of life that could wonder about their own origins. And that transformation continues today. Our planet is still cooling, still changing, still hosting an ongoing experiment in biological complexity that began in those alien seas more than 3.5 billion years ago. Good night, Archean Eon. Good night, ancient Earth. And good night to all of you, wherever you are in this long, slow, magnificent story that connects us all. But before we close this chapter completely, let's linger just a moment longer in that ancient world, because there's something profound about imagining ourselves as observers in that alien time, something that helps us understand not just where we came from, but what persistence really means on a planetary scale. Picture it once more. You're standing on the shore of an Archean sea, somehow protected from the toxic air and deadly radiation. The water before you is green-tinged with dissolved iron, lapping against black volcanic rock under a sky that shifts between orange and pink depending on the methane concentration. The silence is deeper than anything you've ever experienced. No birds, no insects, no rustle of vegetation, just the geological sounds of a planet still finding its rhythm. Wind across bare stone, waves against basalt, the distant rumble of volcanic activity that never quite stops. And yet, beneath that alien surface, in the warm shallows where sunlight penetrates through the hazy atmosphere, something remarkable is happening. Microbial mats are growing, layer by microscopic layer. Oxygen is being produced, molecule by molecule, even though it's immediately consumed by the iron-rich water. Stromatolites are building themselves up over centuries and millennia, creating the first architectural achievements in Earth's history. Not monuments to anything, not symbols or markers, just the persistent accumulation of biological activity over deep time. This is where patience was invented in a sense, not the human patience of waiting for something specific to happen, but the deeper patience of geological processes, the willingness of the universe to let things develop slowly, to allow complexity to emerge through repetition rather than sudden innovation. The Archean teaches us that the most fundamental changes often happen so slowly that they're invisible to any individual observer. No single microbe lived long enough to see the atmosphere change. No individual stromatolite building community witnessed the great transformation from anoxic to oxygenated oceans. But the change happened anyway, through the accumulation of countless small actions over unimaginable spans of time. Every photosynthetic reaction, every grain of sediment trapped by a microbial mat, every iron atom pulled out of solution by a trace of oxygen, all of it added up to something genuinely transformative. And perhaps that's the most important lesson the Archean offers us today. In our fast-paced world of instant communication and rapid change, it's easy to forget that the most profound transformations often work on timescales that dwarf human experience. The atmosphere we breathe, the continents we live on, the magnetic field that protects us, all of these emerged through processes that operated patiently over hundreds of millions or billions of years. They remind us that some problems can only be solved through persistence. Some changes can only happen through time. The microbes of the Archean didn't set out to create an oxygen-rich atmosphere. They were simply doing what they needed to do to survive and reproduce, capturing sunlight, building organic molecules, releasing oxygen as waste. But their collective activity, maintained over geological time, eventually changed the entire planet. In the same way, the continental cratons didn't form because the Earth was trying to build stable land masses. They emerged through the repeated operation of volcanic processes, crustal thickening, and tectonic collision, geological events that followed physical laws without any ultimate purpose or plan. But the result was something that could persist, something that could serve as a foundation for everything that followed. This is how complexity builds in natural systems, not through design or intention, but through the patient operation of simple processes over vast scales of time and space. The Archean world was simple in its components: rock, water, simple gases, single-celled organisms, but complex in its interactions and ultimately revolutionary in its consequences. And if we look closely at our own world today, we can see the same principles still operating. Climate systems, ecological networks, evolutionary processes, all of them work on timescales that extend far beyond human lifespans, following rules that emerged during that ancient time when life first began to reshape its planetary environment. The carbon cycle that regulates our climate today is the direct descendant of the carbon cycling that began in Archean seas. The oxygen cycle that maintains our breathable atmosphere started with those first hesitant experiments in photosynthesis more than 3.5 billion years ago. The plate tectonic processes that continue to reshape our continents operate according to principles established when the first protocontinents began to collide and merge during the late Archean. We are living in a world that was fundamentally shaped by that ancient time, even though almost nothing visible from the Archean survives on Earth's surface today. The rocks have been recycled, the atmospheric composition has changed completely, the forms of life have been replaced by something infinitely more complex. But the underlying patterns, the fundamental processes, the basic rules of how a planet can host and sustain life, all of that was worked out during those first 2 billion years of Earth's history, when the world was alien beyond our imagination, but already displaying the characteristics that would eventually make our existence possible. When we study the Archean, we're not just learning about the distant past. We're learning about the deep structures that continue to govern our world today. We're discovering the roots of the processes that still shape climate, still drive evolution, still regulate the chemistry of air and ocean. And perhaps most importantly, we're gaining perspective on the kinds of changes that are possible over truly long timescales. The transformation from an anoxic to an oxygenated planet happened gradually, but it was also complete and irreversible. Once oxygen began to accumulate in the atmosphere, there was no going back to the old chemistry. The organisms that had evolved to thrive in an oxygen-free world either adapted to the new conditions, found refuge in environments that remained anoxic, or disappeared entirely, the planet as a whole shifted to a new stable state, not necessarily better or worse than what came before, but fundamentally different and capable of supporting forms of life that had never existed before. This kind of planetary scale transition has happened multiple times in Earth's history. The initial formation of the atmosphere and oceans, the emergence of photosynthesis, the Great Oxidation Event, the development of multicellular life, the colonization of land by plants and animals. Each transition opened new possibilities while closing off others. Each created opportunities for some forms of life while making the world uninhabitable for others. And each took place over timescales that make human history look like a brief moment. Understanding these deep patterns doesn't just satisfy our curiosity about the past, it helps us think more clearly about the kinds of changes that might be possible in the future and the timescales on which they might operate. It reminds us that the Earth we know today is not a permanent, unchanging baseline, but rather one moment in a long story of planetary evolution that began billions of years ago and will continue for billions of years into the future. The Archean world seems alien to us now, but it was perfectly normal for its time. The creatures that lived in it were well adapted to its conditions. The processes that shaped it were stable and sustainable over geological time. In the same way, our current world, with its oxygen-rich atmosphere, its complex ecosystems, its ice caps and forests and coral reefs, represents just one possible configuration of a habitable planet. It feels permanent and natural to us because it's the only world we've ever known, but it's actually quite recent in geological terms and will certainly change over the vast timescales that lie ahead. That doesn't make it less valuable or less worthy of protection. If anything, understanding the deep history of our planet makes the current moment more precious because we can see how rare and special the conditions are that allow complex life like ours to exist. The Archean reminds us that for most of Earth's history, the planet was inhabited only by microbes. Multicellular life is a relatively recent innovation. Intelligence, consciousness, and technology are even more recent. The window of time during which beings like us can exist and wonder about their own origins is astronomically brief compared to the deep history of the planet. But that brevity doesn't diminish the significance of what we've become. If anything, it makes the emergence of life capable of understanding its own history seem even more remarkable. We are the universe becoming conscious of itself, the Earth developing the ability to study its own past and contemplate its own future. The microbes of the Archean built stromatolites without knowing they were creating some of the first fossils. They produced oxygen without understanding they were transforming the atmosphere. They established the biogeochemical cycles without realizing they were laying the foundation for everything that would follow. But we can know these things. We can read the story written in stone. We can trace our lineage back through billions of years to those first experiments in life. We can understand at least partially how we came to be and what it took to make our existence possible. That understanding carries with it a kind of responsibility, not just to preserve the world we've inherited, but to appreciate its deep history and remarkable complexity, to recognize that we are part of a story much larger and older than human civilization, a story that connects us to every living thing on Earth and to the planet itself. The Archean teaches us humility in the face of deep time. It shows us how small and recent we are in the grand scheme of planetary history, but it also shows us that small things can have enormous consequences when they persist long enough. A single photosynthetic reaction is insignificant. Billions of them, repeated over millions of years, change the composition of the atmosphere. A single grain of sediment trapped by a microbial mat doesn't matter. Countless grains, accumulated over geological time, built structures that we can still see today. In the same way, the small actions we take today, the choices we make about energy, about consumption, about how we treat the natural world, may seem insignificant in isolation, but when multiplied across billions of people and extended over decades or centuries, they have the potential to influence the trajectory of planetary change. We can't know exactly what the Earth will look like millions or billions of years from now. The timescales are too vast, the variables too complex, the possibilities too numerous to predict with certainty. But we can be confident that change will continue, that life will adapt and evolve, that the planet will keep writing its story in rock and ice and the chemistry of air and ocean. And we can choose to be conscious participants in that ongoing story rather than passive observers. We can try to understand the deep patterns that govern planetary change. We can work to preserve the conditions that allow complex life to flourish. We can approach the future with the same patience and persistence that characterized life during the Archean. Because in the end, the most important lesson from that ancient world might be the simplest one, that life finds a way to persist, even under conditions that seem impossible. That complexity can emerge from simplicity, given enough time. That small, repeated actions can accumulate into transformative change. The microbes that built the first stromatolites had no grand vision of what they were creating. They were just doing what life does, persisting, adapting, making the best use of available resources. But their patient work over vast stretches of time laid the foundation for everything that followed. Perhaps that's enough for any of us to do what we can with what we have, to persist in the face of uncertainty, to trust that small actions repeated faithfully can contribute to something larger than ourselves. The Archean world reminds us that even in the most alien and hostile conditions, life found ways not just to survive but to thrive and eventually to transform its entire environment. That capacity for persistence, for adaptation, for patient construction of something better, that's our inheritance from those ancient seas. It's what connects us across billions of years to the first microbes that captured sunlight and released oxygen into an atmosphere that couldn't yet sustain anything like us. It's what gives us hope that whatever challenges lie ahead, life will find ways to persist and adapt and continue the long, slow work of building complexity from simplicity. The Archean isn't just the distant past. It's the foundation everything else stands on, including us. Its lessons about patience, persistence, and the power of small actions repeated over time are as relevant today as they were 3.5 billion years ago. And so we carry its story forward, conscious inheritors of a process that began in silence and transformed the world through nothing more dramatic than the patient accumulation of change. The Archean taught the Earth how to host life. Now it's teaching us how to understand and appreciate the long story we're part of. That story continues today. In every breath we take of oxygen produced by photosynthesis, in every step we take on continents built from Archean cratons, under the protection of a magnetic field that has been operating since before complex life existed. We are the latest chapter in a book that began writing itself in those ancient seas, and like all the chapters that came before, our contribution will be measured not in dramatic gestures, but in the patient accumulation of small choices, repeated faithfully over time, building towards something we can't yet fully imagine, but can trust will be worthy of the foundation that made it possible. The Archean waits behind everything we know, quiet and persistent as ever, reminding us that the most profound changes often happen slowly, that complexity emerges from simplicity, and that life, however strange or familiar it might become, always finds a way to continue the story. Good night, ancient Earth. Thank you for the foundation. Thank you for the patience. Thank you for showing us that time itself can be a kind of creative force, and that persistence, more than anything else, is what allows impossible things to become possible. The story continues. Hello again, and welcome to part 2, where we take our time with the deep questions and let science unfold at its own natural pace. If you're returning from our first journey into the Archean, welcome back to this ancient world. If you're just joining us now, you're stepping into the middle of Earth's earliest story, a time so remote and alien that it challenges everything we think we know about what a living planet looks like. We've already explored the foundations of that primordial world, the toxic atmosphere, the iron-green oceans, the constant volcanism, and the first tentative experiments in life that would eventually transform everything. But there's so much more to uncover in these ancient depths of time. The Archean lasted for over 1 billion years, which means it encompasses changes and developments that dwarf the entire history of complex life on Earth. If you're finding yourself drawn into this deep time perspective, if you're enjoying this slower approach to understanding our planet's history, I'd love it if you could hit that like button. It really helps the channel reach others who might appreciate these longer explorations into Earth's past. And if this kind of content resonates with you, if you enjoy diving deep into the foundational stories that shaped our world, consider subscribing. We'll continue exploring these vast timescales and the patient processes that built the planet we call home. Tonight, we're going deeper into the Archean world, not just visiting it as curious observers, but truly inhabiting its strange rhythms and alien possibilities. We're going to explore what it meant for life to exist in a world without seasons as we know them, without weather patterns we'd recognize, without any of the biological cycles that seem so fundamental to the way we understand living systems today. We're going to follow the slow evolution of Earth's interior, watching as the planet's internal heat engine began to settle into the patterns that continue today. We'll trace the gradual thickening of the atmosphere and the subtle changes in ocean chemistry that set the stage for everything that followed. And we're going to spend time with the real architects of the Archean world, the microorganisms that not only survived in conditions that would be instantly lethal to us, but thrived, diversified, and began the slow work of planetary transformation that continues to this day. Because while the first part of our Archean exploration focused on the broad strokes, the basic conditions, the fundamental processes, the overall character of that ancient time, this second part will take us deeper into the details. The intricate mechanisms, the subtle interactions, the patient work of chemistry and biology, operating over timescales that stretch human imagination. We'll discover how the first complex organic molecules formed in the primordial oceans, how the earliest metabolic pathways established themselves, and how life began to organize itself into the kinds of communities that could persist and grow despite the harsh conditions. We'll explore the role of clay minerals and metal surfaces in catalyzing the chemical reactions that led to biology. We'll examine the gradual development of cellular structures and the emergence of the first truly stable forms of heredity. And we'll trace the slow accumulation of oxygen, not just as a waste product, but as a molecule that would eventually enable entirely new forms of life and fundamentally alter the trajectory of planetary evolution. But perhaps most importantly, we'll develop a deeper appreciation for the timescales involved in all of these processes, the patient, incremental nature of change during the Archean, and the way that small modifications repeated countless times over hundreds of millions of years could eventually produce results that were nothing short of revolutionary. The Archean teaches us that evolution, both biological and geological, is not primarily about dramatic events or sudden leaps forward. It's about persistence, about the accumulation of tiny changes, about the power of simple processes operating consistently over vast periods of time. This is a different kind of story than we're used to hearing. It's not driven by conflict or crisis, by heroes and villains, by dramatic reversals and climactic moments. It's driven by chemistry and physics, by the patient operation of natural laws, by the tendency of complex systems to organize themselves in increasingly sophisticated ways. And yet, it's also the most important story ever told, because it's the story of how we got here. Everything we are, everything we depend on, everything we take for granted about the world around us can be traced back to processes that began during this strange, remote, alien time. So let's return to that world, not as tourists passing through, but as students trying to understand the deep principles that govern planetary development. Let's immerse ourselves in the rhythms of the Archean and try to feel what it would have been like to exist in a universe where time moved differently, where change happened slowly, and where the future was being built molecule by molecule in the dark waters of ancient seas. The story continues. In the perpetual twilight of the Archean atmosphere, where methane haze scattered sunlight into strange colors and temperatures rose and fell according to volcanic moods. Rather than familiar seasons, time itself seemed to move differently than it does today. Not just because the days were shorter, though they were spinning by in roughly 14 hours, but because the very concept of change operated on such different scales. We think of evolution as something that happens over millions of years, which is fast by geological standards but still almost incomprehensibly slow from a human perspective. But Archean evolution was even more gradual, more patient. The environmental pressures were different, the populations were smaller, and the chemical constraints were so severe that most evolutionary experiments simply couldn't survive long enough to establish themselves. And yet, within those constraints, something remarkable was happening. Life was learning the fundamental skills that would serve it for the next 4 billion years. How to capture and store energy, how to build complex molecules from simple ingredients, how to maintain organization in the face of entropy, how to reproduce accurately while still allowing for variation and adaptation. These weren't abstract lessons or theoretical principles, they were practical problems that had to be solved by actual organisms living in actual environments, using whatever materials and energy sources were available. The solutions that emerged during the Archean formed the basic toolkit that all subsequent life would build upon. Consider the challenge of energy capture, for example. In our modern world, photosynthesis seems like the obvious solution. Use sunlight to drive chemical reactions that build organic molecules from carbon dioxide and water. But in the Archean, that solution was far from obvious. The atmosphere was thick with haze that scattered and absorbed much of the incoming light. The water was full of dissolved metals that could interfere with delicate biological machinery. And most importantly, the chemistry required for splitting water molecules was extraordinarily complex and energetically expensive. Early photosynthetic organisms had to evolve sophisticated molecular mechanisms for capturing photons, transferring their energy through chains of specialized proteins, and using that energy to drive thermodynamically unfavorable reactions. They had to develop systems for protecting themselves from the toxic oxygen they produced as a byproduct. They had to create structures that could channel light efficiently while remaining stable in harsh chemical conditions. All of this took time, not years or decades, but hundreds of millions of years of gradual refinement and optimization. Each small improvement in efficiency or stability would spread slowly through microbial populations, conferring slight advantages that accumulated over geological timescales. The result was a biological energy capture system so sophisticated that we still don't fully understand how it works. Even with all our modern scientific instruments and analytical techniques, the molecular machinery of photosynthesis represents one of the great achievements of Archean evolution, a complex solution to a fundamental problem that has remained essentially unchanged for over 3 billion years. But photosynthesis was just one of many energy strategies that emerged during this period. In the deep ocean, around hydrothermal vents where superheated water-rich and dissolved minerals poured from cracks in the seafloor, life developed equally sophisticated mechanisms for extracting energy from chemical reactions. These chemosynthetic organisms learned to harvest electrons from hydrogen sulfide, methane, ammonia, and other reduced compounds. They built molecular machines that could operate at temperatures that would denature most proteins in water so acidic or alkaline that it would dissolve organic molecules under pressures that would crush most cellular structures. Each of these extreme environments required its own specialized solutions. Organisms living in high-temperature environments developed heat-resistant proteins with unusual amino acid sequences and more robust folding patterns. Those adapting to high pressure evolved cellular structures that could maintain their integrity under crushing force. Microbes coping with extreme acidity or alkalinity created membrane systems that could maintain pH balance despite hostile external conditions. The diversity of metabolic strategies that emerged during the Archean is staggering. Some organisms learned to breathe sulfate instead of oxygen, reducing it to hydrogen sulfide. Others figured out how to use nitrates or nitrites as electron acceptors. Still others developed pathways for metabolizing methane, hydrogen gas, or even complex organic compounds that had formed through non-biological processes. What's remarkable is that most of these metabolic pathways are still in use today. The biochemical innovations of the Archean didn't become obsolete when conditions changed. They became the foundation for more complex systems. Modern organisms still use modified versions of Archean metabolic machinery, even in environments that would have been impossible during that ancient time. This speaks to something profound about the nature of evolutionary innovation. The solutions that worked during the Archean were not just good enough for their time, they were so fundamentally sound that they continue to serve as the basis for life even under radically different conditions. But metabolism was only part of the challenge. Even more fundamental was the question of how to maintain organizational integrity over time. How do you build a system that can persist, reproduce, and evolve while constantly exchanging materials with its environment? This is where the development of cellular membranes became crucial. In our world today, every living cell is surrounded by a lipid bilayer, a double layer of fatty molecules that serves as a selective barrier between the inside and outside of the cell. These membranes allow cells to maintain different chemical conditions inside and outside, to control what enters and exits, and to create the kind of stable internal environment that complex biochemistry requires. But during the Archean, building stable membranes was extraordinarily challenging. The lipid molecules that work well in modern cells would have been unstable under Archean conditions. The temperature fluctuations, the chemical environment, the high levels of radiation, all of these would have quickly destroyed the delicate molecular structures that define cellular boundaries today. Early life had to develop alternative membrane chemistries that could function under much harsher conditions. Some Archean organisms evolved membranes based on ether-linked lipids instead of the ester-linked lipids used by modern cells. These ether bonds are more chemically stable and less prone to breakdown under extreme conditions. Others developed membranes with unusual fatty acid compositions that remained flexible at high temperatures but didn't become too fluid to maintain barrier function. Still others created hybrid systems that combined lipids with proteins or other molecules to create more robust boundary structures. The evolution of stable cellular membranes was a gradual process that took hundreds of millions of years. Each improvement in membrane stability or selectivity would have provided advantages that could spread through populations over geological time. The organisms with better membranes could maintain more sophisticated internal chemistry, survive in more challenging environments, and reproduce more reliably. Eventually, this led to the development of cellular structures that were sophisticated enough to support the complex biochemistry required for life as we know it. But even these early cells were profoundly different from modern ones. They lacked nuclei, organelles, and most of the internal structures that we associate with cellular organization today. Instead, they relied on different principles of organization. Some used protein-based scaffolding to organize their internal chemistry. Others employed mineral surfaces or organic polymers to concentrate and organize their molecular machinery. The details of these ancient organizational systems are still being worked out by researchers studying the molecular fossils and chemical signatures preserved in Archean rocks. But what's clear is that early life found ways to create order and maintain complexity, even without the sophisticated cellular machinery that we depend on today. This speaks to the resourcefulness and adaptability that characterized Archean life. These organisms couldn't rely on established solutions or well-tested biological strategies. They had to innovate constantly, experimenting with new approaches to fundamental biological problems. Many of these experiments failed, leaving no trace in the geological record, but some succeeded, establishing patterns and principles that would shape the entire future of life on Earth. The successful innovations of the Archean were those that could operate reliably under harsh conditions, that were chemically robust enough to persist over geological time, and that were flexible enough to serve as the foundation for more complex systems. These criteria, Reliability, robustness, and flexibility became the basic requirements for biological success, not just during the Archean but throughout the entire history of life on Earth. They remain the fundamental principles that govern biological evolution today. The Archean was the testing ground where life learned these principles through direct experience. The organisms that survived this testing established the basic rules that all subsequent life would have to follow. But the Archean didn't just shape biology, it also established many of the geological processes that continue to govern our planet today: the patterns of crustal formation, the cycles of erosion and sedimentation, the basic structure of plate tectonics. All of these emerged during this ancient time. The Archean Earth was much hotter than today's planet, both at the surface and in the interior. The mantle was more active, driving more vigorous convection patterns that brought heat more efficiently to the surface. This resulted in much higher rates of volcanic activity, more extensive lava flows, and more rapid recycling of crustal materials. But this high level of geological activity also meant that crustal structures had difficulty achieving long-term stability. The thin, hot crust was easily deformed by tectonic forces. Entire regions could be uplifted, eroded down, or subducted back into the mantle over relatively short geological timescales. The challenge for early continental formation was finding ways to create crustal blocks that were thick enough and buoyant enough to resist subduction. This required the development of new rock types, particularly felsic rocks rich in silica and aluminum that were less dense than the mafic rocks that dominated the early crust. The formation of these felsic rocks was a slow process that required multiple cycles of melting, crystallization, and chemical differentiation. Each cycle would produce rocks that were slightly more evolved in their chemical composition, slightly more enriched in the light elements that make continental crust buoyant. Over hundreds of millions of years, this process gradually built up the first stable continental blocks, the cratons that still form the cores of modern continents. These ancient cratons were small compared to modern continents, but they represented the first truly permanent features on Earth's surface. The formation of stable continental crust had profound implications for both geology and biology. It provided elevated surfaces that could support different kinds of weathering processes. It created shallow marine environments around continental margins where life could experiment with new strategies for survival and growth. Most importantly, it began to establish the kind of stable platforms that could support more complex geological and biological processes over long time periods. But the development of continental crust was just one aspect of the broader geological evolution that characterized the Archean. The ocean basins were also undergoing fundamental changes, as the planet's internal heat budget gradually declined, and the mechanisms of plate tectonics began to take their modern form. During the early Archean, the ocean floor was probably recycled much more rapidly than it is today. The high internal heat drove more active seafloor spreading, which meant that new oceanic crust was created quickly and old crust was subducted back into the mantle on relatively short timescales. This rapid recycling had important consequences for ocean chemistry. It meant that the composition of seawater was more directly connected to the chemistry of the mantle than it is today. Dissolved metals, gases, and other compounds were continuously being added to the ocean through volcanic activity and hydrothermal circulation. At the same time, the rapid recycling meant that materials deposited on the sea floor, including the products of early biological activity, were quickly buried and incorporated back into the mantle. This made it difficult for biological processes to have a lasting impact on global geochemical cycles. But as the Archean progressed and the planet's internal heat gradually declined, these processes began to slow down. Seafloor spreading became less vigorous. Continental crust became thicker and more stable. The residence time of materials in the ocean increased. These changes created opportunities for biology to have more lasting effects on planetary chemistry. Instead of being quickly recycled back into the mantle, the products of biological activity could accumulate in sedimentary rocks and begin to influence global geochemical cycles. This was the beginning of the transition from a planet dominated by geological processes to one where biology began to play an increasingly important role in regulating environmental conditions. The timing of this transition was crucial. It happened slowly enough that life had time to adapt to changing conditions, but quickly enough that biological innovations could begin to influence the planetary environment on timescales that were relevant to evolution. If the transition had happened too quickly, life might not have been able to keep up with the changing conditions. If it had happened too slowly, biological processes might never have gained enough influence to begin reshaping the planetary environment. The actual pace of change during the Archean was somewhere in between, fast enough to drive innovation and adaptation, but slow enough to allow for the gradual accumulation of changes that would eventually transform the planet. This balance between stability and change, between conservation and innovation, became one of the defining characteristics of Earth as a living planet. It established the dynamic equilibrium that has allowed life and environment to co-evolve over billions of years. The Archean was the crucible where this balance was first established, where life learned to influence its environment and the environment learned to support increasingly complex forms of life. The lessons learned during this ancient time continue to govern the relationship between life and planet today. They remind us that the most fundamental changes often happen slowly, through the patient accumulation of small modifications over vast periods of time. They also remind us that innovation and conservation must work together. The biological and geological innovations of the Archean were successful because they built upon reliable foundations while gradually exploring new possibilities. This pattern, conservative foundations supporting innovative superstructures, became the template for all subsequent evolution, both biological and geological. Understanding this pattern helps us appreciate both the stability and the dynamism of our modern world, the air we breathe, the continents we live on, the cycles that regulate our climate. All of these depend on foundations that were laid during the Archean, but they also continue to evolve and adapt in response to changing conditions. The Archean teaches us that change and stability are not opposites, but partners in the long dance of planetary evolution. The most successful innovations are those that enhance stability rather than undermining it, that build upon existing foundations rather than replacing them entirely. This perspective has profound implications for how we think about our own role in the ongoing story of planetary evolution. We are part of a system that has been developing for over 4 billion years, guided by principles that were established during the Archean and refined through countless cycles of innovation and selection. Our challenge is to learn how to work with these principles rather than against them, to find ways to support the long-term stability of the systems we depend on while continuing to innovate and adapt to changing conditions. The Archean world seems impossibly remote and alien, but its lessons are surprisingly relevant to the challenges we face today. It reminds us that the most important work is often slow and patient, that small changes can have enormous consequences over time, and that true sustainability requires building upon reliable foundations rather than constantly starting over. These insights don't provide easy answers to contemporary problems, but they do provide a valuable perspective, a reminder that we are part of something much larger and older than human civilization, something that has successfully navigated countless challenges over billions of years. The microorganisms of the Archean faced environmental conditions far more challenging than anything we encounter today, yet they not only survived but established the foundations for all subsequent life. Their success was based on patience, persistence, and the gradual accumulation of innovations that enhanced rather than undermined long-term stability. Perhaps there are lessons there for us as we face our own planetary challenges. Not simple solutions, but approaches, ways of thinking about time and change, and the relationship between innovation and conservation that have been tested over the longest possible timescales. The Archean continues to speak to us across billions of years, reminding us that we are part of an ongoing experiment that began in those ancient seas and continues today in every breath we take, every step we walk on continents built from Archean cratons, every moment we exist under the protection of systems that were first established during that remote and remarkable time. The conversation between life and planet that began during the Archean has never stopped. It continues in the chemistry of our cells, in the cycles that regulate our atmosphere, in the slow but persistent evolution of the systems we depend on. We are the most recent participants in this ancient conversation, but we are not separate from it. We are part of it, shaped by it, dependent on the foundations it established. Our role is not to control or dominate this conversation, but to understand it well enough to participate wisely in its ongoing development. The Archean reminds us that this is possible, that complex, sophisticated systems can emerge from simple beginnings through patient, persistent work over vast periods of time. It gives us hope that the challenges we face today, however daunting they might seem, are not beyond the capacity of the systems we are part of to address and resolve. But it also reminds us that the timescales involved in planetary-level change are much longer than human lifetimes or political cycles or economic quarters. The work we do today may not produce visible results for decades or centuries, but that doesn't make it less important. The microorganisms of the Archean worked for hundreds of millions of years to transform the atmosphere, never seeing the final result of their efforts, but their patient work made our existence possible. Perhaps our own patient work will make possible forms of life and consciousness that we can't yet imagine. The story that began in the Archean seas continues today, and we are part of it. That's both a tremendous responsibility and a profound source of meaning. We are connected across deep time to the first experiments in life, and forward into an uncertain but potentially remarkable future. The Archean teaches us that this is how change really works, slowly, patiently, through the accumulation of countless small actions over timescales that dwarf individual lifespans. It's not a glamorous vision of change, but it's a realistic one, and it's the vision that has actually worked to create the world we inhabit today. Perhaps that's enough to do our part in the ongoing conversation, to contribute what we can to the patient work of building systems that can persist and evolve over the long term. The Archean shows us that this kind of work is possible, that it can succeed even under the most challenging conditions, and that it can produce results far beyond what any individual could achieve alone. The ancient seas where this all began are gone now, replaced by oceans that would be barely recognizable to Archean microorganisms, but the principles established during that time persist. The conversation continues, and we are part of it, carrying forward innovations that began billions of years ago and adding our own contributions to a story that will continue long after we are gone. That continuity across deep time is perhaps the most remarkable aspect of the Archean legacy. It reminds us that we are not isolated in the present moment, but connected through unbroken chains of causation to the deepest past and the furthest future. The oxygen we breathe was first produced by Archean cyanobacteria. The continents we live on have cores that formed during Archean crustal processes. The biochemical pathways that power our cells are descendants of metabolic innovations that emerged in Archean seas. We carry the Archean forward in everything we do, and everything we do will influence the trajectory of the systems that began during that ancient time. This is both humbling and inspiring, a reminder that we are part of something much larger than ourselves, but also that our actions matter on timescales far longer than we usually consider. The Archean Eon lasted over 1 billion years. Our species has existed for a few 100,000 years. Our civilization is only a few thousand years old. In one sense, we are barely a blip in the long story that began during the Archean. But in another sense, we represent something genuinely new in that story, the emergence of consciousness capable of understanding its own origins and contemplating its own future. We are the part of the universe that has become aware of itself, capable of reading the story written in ancient rocks and extrapolating from deep time processes to imagine possible futures. This is an unprecedented development in the 4 billion-year history of life on Earth. Never before has any form of life been capable of understanding the planetary systems it depends on, or of consciously influencing those systems based on long-term projections of their behavior. This capability brings with it new responsibilities and new possibilities. We can choose to work with planetary systems rather than against them. We can make decisions based on understanding of deep time processes rather than just short-term convenience. We can participate consciously in the ongoing evolution of the systems we are part of. The Archean provides a template for how this kind of conscious participation might work. The organisms of that time were successful because they found ways to work with the constraints and opportunities provided by their environment, rather than trying to transcend or overcome them. They built systems that were robust enough to persist under challenging conditions, flexible enough to adapt to changing circumstances, and efficient enough to make productive use of limited resources. These remain the fundamental requirements for long-term success in any complex system. They were true during the Archean, and they remain true today. The challenge for us is to learn how to apply these principles at scales and timescales that are relevant to our own situation, while drawing on the accumulated wisdom of 4 billion years of planetary evolution. This is not a simple task, but it's not an impossible one. The Archean shows us that complex problems can be solved through patient work over long periods of time, that innovative solutions can emerge from careful attention to fundamental principles, and that systems can evolve in ways that enhance rather than undermine their long-term stability. We have advantages that Archean organisms lacked: consciousness, communication, the ability to learn from the experiences of others, and to plan for future contingencies. But we also face challenges that they never encountered: the need to coordinate behavior across billions of individuals, to manage resources on a planetary scale, to balance short-term needs with long-term sustainability. The principles established during the Archean can guide us in meeting these challenges, but they cannot solve them for us. That work remains to be done by us in our time with the knowledge and capabilities available to us. But we don't have to do this work alone or without guidance. We are part of systems that have been evolving for billions of years, systems that have successfully navigated countless challenges and transitions. We can learn from their successes and failures, build upon their innovations, and contribute our own insights to their ongoing development. The Archean reminds us that this kind of evolutionary work is possible, that complex challenges can be met through persistent effort over appropriate timescales, and that the results can be transformative in ways that are difficult to anticipate, but deeply meaningful once they emerge. Perhaps most importantly, it reminds us that we are not separate from the natural world, but part of it. The same processes that shaped Archean microorganisms continue to shape us. The same principles that governed their success continue to govern ours. We are not outside observers of planetary evolution, but active participants in its ongoing development. Our thoughts and decisions and actions are part of the natural processes that shape the world. Our success depends on learning to align our activities with the deeper patterns that have guided planetary evolution for billions of years. This is not about returning to some imagined state of primitive simplicity, but about finding ways to participate constructively in complex systems that extend far beyond our direct control or complete understanding. The Archean organisms that built the first stromatolites had no grand plan for transforming the planet's atmosphere. They were simply doing what they needed to do to survive and reproduce in their immediate environment. But their collective activities, sustained over geological time, had consequences that reshaped the entire planet. Perhaps our own individual actions, guided by understanding of long-term processes and coordinated through conscious communication and planning, can contribute to planetary developments that are equally transformative but more intentional in their design. This is the challenge and the opportunity that the Archean legacy presents to us. We have inherited systems of extraordinary sophistication and resilience, built through billions of years of patient evolutionary work. Our task is to learn how to participate in the ongoing development of these systems in ways that enhance rather than undermine their long-term stability and productivity. The stakes are high, but the precedent is encouraging. Life has successfully navigated planetary-scale challenges before, under conditions far more difficult than anything we face today. The innovations that emerged from those challenges became the foundations for everything that followed, including us. Our innovations, in turn, will become part of the foundation for whatever follows us. The Archean teaches us that this is how evolution works, not through final solutions, but through ongoing adaptations that enhance the capacity of systems to persist and develop over time. We are part of that ongoing process, inheritors of its past achievements and contributors to its future possibilities. The Archean began the conversation between life and planet that continues in our thoughts and actions today. Understanding that conversation, learning to participate in it thoughtfully and constructively, may be the most important work we can do, not because we can control its outcomes, but because we can influence them in ways that support the long-term flourishing of the systems we are part of. The Archean shows us that this kind of constructive influence is possible, even under the most challenging conditions. It gives us both a template for how such work might proceed and the confidence that it can succeed. The rest is up to us, to learn, to adapt, to innovate within the constraints and opportunities provided by our planetary inheritance, and to contribute our own chapter to the ongoing story that began in those ancient seas and continues wherever life meets environment in the patient work of building sustainable futures. If you followed this journey through deep time with us, if these explorations of planetary history resonate with the way you think about our place in the larger story of Earth, I'd be grateful if you could like this video and let me know in the comments. And if this slower, more contemplative approach to understanding our world appeals to you, consider subscribing. There are more chapters of this story to explore, more connections to uncover between past and present, more lessons to learn from the deep archives of planetary memory. The conversation between life and Earth that began in the Archean continues today, in every breath, every heartbeat, every moment of consciousness aware of its own origins. We are all part of that conversation, and the more we understand about its history, the better we can participate in writing its future chapters. The Archean waits behind everything we know, patient as always, reminding us that the most profound changes often happen slowly, and that persistence, more than anything else, is what allows impossible things to become the foundations of worlds we can barely imagine. Thank you for taking this time to look backward through billions of years, to appreciate the deep foundations that make our present moment possible, and to consider what we might contribute to the long story that will continue after we're gone. The ancient seas are gone, but their legacy flows through everything we are and everything we might become. The story continues. But let's not leave the Archean just yet. There's something almost hypnotic about that ancient world, something that draws us back again and again to contemplate its alien rhythms and impossible timescales. Perhaps it's because the Archean represents a kind of purity, a time when the fundamental processes of planetary evolution operated without the complications and distractions that would come later. No predators stalking prey through shallow waters, no competition between complex organisms for limited resources, no mass extinctions triggered by asteroid impacts or volcanic catastrophes, just chemistry and physics, operating patiently according to their own internal logic, building complexity from simplicity one reaction at a time. The silence of that world is profound in ways we're only beginning to appreciate. Not just the absence of biological sounds, no bird songs, no insect hums, no rustle of leaves, but the deeper silence of a world where consciousness had not yet emerged to observe and interpret its own existence. For over 1 billion years, the Earth was a planet without observers, without minds capable of wonder or curiosity or the desire to understand. The stromatolites built themselves up layer by layer without anyone to marvel at their construction. The first oxygen molecules were released into the atmosphere without anyone to appreciate the revolutionary nature of that simple chemical process. The volcanic islands rose from the sea and were worn down by erosion without anyone to witness their temporary existence. The tides pulled by that closer moon rose and fell in their enormous cycles without anyone to calculate their periods or predict their effects. This was a world of pure process, systems operating according to physical laws without the self-reflection that we bring to our observations of nature today. And yet, it was not a world without direction or purpose. The processes that operated during the Archean were building towards something, even if that something could not be anticipated or planned. Every photosynthetic reaction that released oxygen into the water was preparing the way for forms of life that could use oxygen for metabolism. Every grain of sediment trapped by a microbial mat was contributing to the construction of geological structures that would preserve the history of early life for billions of years. Every cycle of volcanic outgassing and chemical weathering was participating in the gradual regulation of planetary temperature and atmospheric composition. The Archean Earth was unconscious, but it was not purposeless. This raises fascinating questions about the nature of evolution and the emergence of complexity. We're accustomed to thinking of evolution as a process driven by competition and survival, organisms struggling against each other and against their environment, with success measured by reproductive advantage and long-term persistence. But during the Archean, most of these competitive pressures didn't exist yet. There were no predators, no complex food webs, no sophisticated strategies for resource acquisition or territorial defense. Evolution was driven by different forces, primarily the need to maintain chemical organization in the face of thermodynamic entropy, and the gradual exploration of chemical possibilities within the constraints imposed by available energy and raw materials. This was evolution at its most fundamental level, not about gaining advantages over competitors, but about discovering which molecular configurations could persist and reproduce reliably under the harsh conditions of the early Earth. The successful innovations of this period were those that could maintain themselves chemically without external support, that could extract energy from whatever sources were available, and that could pass their organizational patterns on to subsequent generations with enough accuracy to preserve useful innovations while allowing for the variation that drives evolutionary change. These basic requirements, chemical stability, energy acquisition, and accurate reproduction, became the foundation for all subsequent biological evolution. Every living thing today, from the simplest bacterium to the most complex multicellular organism, must meet these same fundamental criteria. But the ways of meeting these criteria have become extraordinarily diverse and sophisticated over the billions of years since the Archean. The simple metabolic pathways that first emerged in those ancient seas have been elaborated into the complex biochemical networks that power modern cells. The basic membrane structures that first allowed cells to maintain chemical organization have evolved into the sophisticated subcellular architectures that make complex life possible. The primitive mechanisms for storing and transmitting genetic information have developed into the elegant molecular systems that preserve and express the accumulated wisdom of billions of years of evolutionary experimentation. Yet all of these modern sophistications are built upon the foundations established during the Archean, the basic chemical logic of metabolism, the fundamental principles of cellular organization, the core mechanisms of genetic inheritance. These were all worked out during that ancient time, when life was just beginning to explore the possibilities available to chemical systems that could maintain and reproduce themselves. Understanding this deep history gives us a different perspective on what life actually is and how it operates. We tend to think of living things as fundamentally different from non-living systems, possessed of some special spark or organizing principle that sets them apart from ordinary matter and energy. But the Archean reminds us that life emerged gradually from non-living chemistry through a long series of incremental steps, each building upon what came before. There was no moment when non-life suddenly became life, no sharp boundary between chemical systems and biological ones. Instead, there was a gradual transition from simple chemical reactions to increasingly complex and organized molecular systems, from systems that could maintain themselves temporarily to those that could reproduce and evolve over time. This perspective doesn't diminish the wonder and significance of life. If anything, it makes biological systems seem even more remarkable. The fact that such extraordinary complexity and sophistication could emerge from ordinary chemistry operating according to physical laws suggests something profound about the creative potential inherent in natural processes. The Archean world was built by chemistry, but it was chemistry of a special kind, chemistry that could learn, adapt, and remember, chemistry that could explore possibilities and preserve the most successful innovations for future use. chemistry that could gradually organize itself into systems of ever-increasing sophistication and capability. This is perhaps the most important lesson the Archean has to offer us, that complexity and sophistication can emerge naturally from simple processes operating over sufficient time. We don't need to invoke special forces or mysterious principles to explain how life emerged and evolved. We just need to appreciate the remarkable creative potential that exists within the natural world when physical processes are allowed to operate persistently over geological timescales. This lesson has implications that extend far beyond biology. It suggests that many of the complex systems we observe in the natural world, from climate patterns to ecological networks to the structure of the universe itself, may have emerged through similar processes of gradual self-organization and emergent complexity. It also suggests approaches to some of the challenges we face in our own technological and social systems. Instead of trying to design complex systems from the top down, we might learn to create conditions that allow complexity to emerge naturally from the bottom up, through the patient operation of simple rules over extended periods of time. The Archean Earth was a masterclass in this kind of bottom-up self-organization. Starting with nothing more than rock, water, and simple gases, it gradually built chemical systems of extraordinary sophistication, geological structures of remarkable stability, and atmospheric compositions that could support increasingly complex forms of life. All of this happened without central planning or conscious direction, through the patient accumulation of small improvements and innovations, each building upon what came before, each contributing to the gradual emergence of something unprecedented and remarkable. This process continues today in every aspect of the natural world, from the molecular machinery of our own cells to the global cycles that regulate our planet's climate. We are part of systems that are still evolving, still exploring possibilities, still building complexity from simplicity through the same kinds of bottom-up processes that characterize the Archean. Understanding these processes doesn't give us control over them. They operate on scales and timescales that extend far beyond our direct influence. But it does give us a framework for thinking about our role within them, and perhaps for finding ways to participate constructively in their ongoing development. The microorganisms of the Archean didn't set out to transform the planetary atmosphere or create the foundations for complex life. They were simply doing what they needed to do to survive and reproduce in their immediate environment. But their collective activities, sustained over geological time, had consequences that extended far beyond their individual lives, or even their immediate ecosystems. They participated, without knowing it, in planetary-scale processes that would reshape the entire future of life on Earth. Perhaps we find ourselves in a similar situation today. Our individual actions and decisions, multiplied across billions of people and extended over decades or centuries, may be contributing to planetary-scale changes whose full implications we can't yet anticipate. The challenge is to learn from the Archean example, to find ways to align our activities with the deep patterns that have guided planetary evolution for billions of years, rather than working against them or ignoring them entirely. This doesn't mean trying to return to some imagined state of primitive simplicity. The complexity and sophistication of modern civilization are part of the natural evolution of planetary systems, just as the complexity of modern cells emerged naturally from the simple chemistry of the Archean. But it does mean recognizing that we are part of systems much larger and older than ourselves, systems that operate according to principles we are only beginning to understand, systems whose long-term health and stability are essential for our own continued existence. The Archean teaches us patience, not passive waiting, but active engagement with processes that unfold over timescales much longer than individual lifespans. It teaches us persistence, the willingness to continue working toward long-term goals even when the results are not immediately visible. Most importantly, it teaches us humility, recognition that we are part of something much greater than ourselves, something that has been developing for billions of years and will continue to develop long after we are gone. This perspective doesn't diminish human significance. If anything, it makes our role in the ongoing story of planetary evolution seem more important and more meaningful. We are the first form of life in Earth's history that has been capable of understanding its own origins and consciously participating in its own further evolution. This represents something genuinely unprecedented in the 4 billion-year history of life on Earth. Never before has the planet hosted organisms capable of reading their own deep history in the geological record, or of making decisions based on long-term projections of planetary change. The emergence of this capability may be as significant as the emergence of photosynthesis or the development of multicellular life. It represents a new phase in the relationship between life and planet, one in which biological systems become conscious of their own role in planetary processes and capable of participating intentionally in their future development. But with this unprecedented capability comes unprecedented responsibility. The Archean organisms that first released oxygen into the atmosphere couldn't anticipate the long-term consequences of their metabolic activities. They were simply following their basic biological programming, doing what they needed to do to survive and reproduce. We, on the other hand, can anticipate at least some of the long-term consequences of our activities. We can study the deep history of planetary change, model possible future scenarios, and make conscious choices about which directions we want to encourage or discourage. This capability brings with it an obligation to think carefully about the long-term implications of our collective activities and to take responsibility for our role in shaping the future trajectory of planetary evolution. The Archean shows us that such long-term thinking is possible and that it can be effective. The patient, persistent work of early life forms sustained over hundreds of millions of years successfully transformed the planetary environment and created conditions that could support more complex forms of life. Our own patient, persistent work, guided by understanding of deep time processes and coordinated through conscious communication and planning, might contribute to planetary developments that are equally transformative but more intentional in their design. This is not a simple or easy task. It requires ways of thinking and acting that extend far beyond our normal temporal horizons. It requires cooperation and coordination on scales and timescales that challenge our usual social and political institutions. But it is not an impossible task. The precedent established during the Archean shows us that complex, sophisticated systems can emerge through the patient accumulation of small contributions over extended periods of time. The microorganisms that built the first stromatolites were individually tiny and short-lived, but their collective activities, sustained over geological time, created structures that we can still study today. Their individual contributions were small, but their cumulative impact was enormous. Perhaps our own individual contributions to the ongoing development of planetary systems will follow a similar pattern. Each of us can do only a small part of the work that needs to be done, but our collective efforts, sustained over appropriate timescales, might produce results that extend far beyond what any of us could achieve individually. The key is to find ways to align our individual activities with the deep patterns that have guided planetary evolution for billions of years, patterns based on patience, persistence, and the gradual accumulation of small improvements over extended periods of time. This requires a different kind of thinking than we're accustomed to, thinking that operates on geological rather than human timescales, that values long-term stability over short-term advantage, that recognizes our dependence on systems much larger and more complex than ourselves. But the Archean shows us that this kind of thinking is not only possible but necessary for long-term success. The organisms that thrived during that ancient time were those that found ways to work with planetary processes rather than against them, that built upon reliable foundations rather than constantly starting over, that contributed to the gradual enhancement of system stability rather than its disruption. These same principles remain relevant today. Our long-term success as a species depends on learning to work with planetary systems rather than against them, to build upon the reliable foundations established over billions of years of evolution. and to contribute to the ongoing enhancement of system stability rather than its degradation. The Archean gives us both a template for how this might work and the confidence that it can succeed. Complex challenges can be met through patient work over appropriate timescales. Innovative solutions can emerge through careful attention to fundamental principles. Systems can evolve in ways that enhance rather than undermine their long-term stability. We have advantages that Archean organisms lacked: consciousness, communication, the ability to learn from the experiences of others, and to plan for future contingencies. But we also face challenges that they never encountered: the need to coordinate behavior across billions of individuals, to manage resources on a planetary scale, to balance short-term needs with long-term sustainability. The principles established during the Archean can guide us in meeting these challenges, but they cannot solve them for us. That work remains to be done by us in our time with the knowledge and capabilities available to us. But we don't have to do this work alone or without precedent. We are part of systems that have been evolving for billions of years, systems that have successfully navigated countless transitions and challenges. We can learn from their successes and failures, build upon their innovations, and contribute our own insights to their ongoing development. The conversation between life and planet that began during the Archean continues today in every breath we take, every decision we make, every moment we spend trying to understand our place in the larger systems we are part of. This conversation is not abstract or theoretical. It is embodied in our daily lives, in the food we eat, and the air we breathe, in the technologies we use, and the institutions we build, in the ways we relate to each other and to the natural world around us. Understanding the deep history of this conversation, appreciating the foundations it has built over billions of years, and recognizing our role as conscious participants in its ongoing development, these may be among the most important tasks we can undertake as individuals and as a species. The Archean is not just ancient history. It is living history, present in every aspect of our current existence, continuing to influence the trajectory of planetary evolution through our thoughts and actions and decisions. We are the descendants of those first microorganisms that learned to capture sunlight and release oxygen into an atmosphere that couldn't yet support complex life. We are the inheritors of systems they built through patient work over geological timescales. We are the continuation of experiments they began in chemical possibility and biological innovation. And we are the first participants in this ancient process who have been capable of understanding what we are part of and consciously choosing how to participate in its further development. This understanding brings with it both tremendous opportunity and tremendous responsibility. We can contribute consciously to the ongoing evolution of planetary systems, working with rather than against the deep patterns that have guided their development for billions of years. But we must do so with the humility and patience that characterized the most successful Archean innovations, recognizing that the most important work often happens slowly, that complex problems require persistent effort over extended periods of time, and that true success is measured not in short-term advantage, but in long-term contribution to system stability and resilience. The Archean began the long experiment in planetary-scale cooperation between life and environment that continues today. Our task is to learn how to participate consciously and constructively in this ongoing experiment, contributing our own innovations while preserving and building upon the reliable foundations established over billions of years. This is work that extends far beyond any individual lifetime, work that will be continued by future generations using knowledge and capabilities we can't yet imagine. But it is work that begins today, in the choices we make and the priorities we set and the ways we think about our relationship to the systems we are part of. The Archean teaches us that such work is possible, that complex challenges can be met through patient effort sustained over appropriate timescales, and that the results can be transformative in ways that exceed our current ability to anticipate or imagine. Perhaps that's enough to begin with. The knowledge that the work is possible, the precedent that it can succeed, and the understanding that we are part of something much larger and more remarkable than we often realize. The ancient seas where it all began are gone now, transformed beyond recognition by billions of years of subsequent evolution. But their legacy lives on in every breath we take, every heartbeat that moves oxygenated blood through our veins, every moment of consciousness that contemplates its own origins and possibilities. We are the Archean's gift to the future, consciousness capable of understanding deep time, intelligence capable of reading the story written in stone, beings capable of participating intentionally in the ongoing development of the systems that made our existence possible. What we do with this gift, how we use these unprecedented capabilities, will help determine the next chapter in the story that began so long ago in those silent seas under alien skies. The conversation continues, and we are part of it. The experiment continues, and we help shape its outcomes. The story continues, and we are both its most recent characters and its newest authors. The Archean waits behind everything we know, patient as always, reminding us that the most profound changes often happen slowly, that persistence is the key to long-term success, and that we are part of something much older, much larger, and much more remarkable than the brief span of human history might suggest. In that patience, in that persistence, in that recognition of our place in the larger story, there we find both the humility and the hope we need to do our part in the ongoing work of building sustainable futures from the reliable foundations of the deep past. The story that began in the Archean continues today and tomorrow and in all the tomorrows yet to come. We are part of that continuing story, and that is both the greatest responsibility and the greatest privilege we could possibly have. The ancient Earth calls to us across billions of years, not with answers but with principles, not with solutions but with approaches, not with certainties but with the confidence that comes from knowing that complex challenges can be met through patient work, sustained over the timescales that truly matter. We are here because the Archean succeeded in its patient work of building foundations. The future will be what it becomes because of the patient work we do in our time, building upon those foundations toward possibilities we can envision but not yet fully understand. The conversation between life and planet that began in those ancient seas continues in our thoughts and actions today. May we prove worthy of the extraordinary inheritance we have received, and may we contribute wisely to the inheritance we leave for those who will continue the conversation after we are gone.